Hello.
Yes, Megan. Am I audible?
Yes, ma'am, you are audible.
Yes, ma'am.
Okay. Okay, then I guess we'll quickly get started. Um, yeah. So, as we discussed yesterday, we'll go with concepts from week 3, vector spaces. And you can ask your questions whenever you have doubts. Is my screen visible?
Yes, ma'am.
Okay. So maybe we will, so weeks 1 and 2 had vectors, matrices, system of linear equations, how to write a system of linear equations in the matrix form and all that. And based on the coefficient matrix, how to find out the number of solutions the system has. So there are only 3 possibilities. Either it has no solution, or it has infinitely many solutions, or it has exactly one solution, a unique solution. So these are the only 3 possibilities. So to find out all this, we used elementary row operations. We converted the matrix to row echelon form, row reduced echelon form and all that. And using all this, we found out the number of solutions, or in fact found out the solutions as well. So, and other methods, when we had the coefficient matrix to be a square matrix, we use the inverse if the inverse existed. And if the inverse exists, then we also use what is called as the Cramer's rule to solve a system of linear equations and all that. So this is all stuff that happened in the first 2 weeks. So from week 3, our actual linear algebra started. So vector spaces. So what is a vector space? When do you say a set with 2 operations plus and dot to be a vector space? What are the conditions?
V1 plus V2.
So first of all, V should be closed.
On addition.
Closed with respect to plus and dot. That is, these are the first 2 conditions. So V1 plus V2 should belong to V for all V1 and V2 in V, and alpha times V should be in V for all alpha, real numbers alpha and vectors V in V. And along with this, we had a set of axioms that had to be satisfied. So with respect to plus, we had 4 axioms. One was it should be commutative. So the order in which you add the vectors shouldn't matter. Associative, again, it is about adding the vectors, order of adding the vectors. So all these conditions should be satisfied for every vector in V. And then there exists a 0 in the vector space. So what is the 0 actually? It is that vector which when added to any other vector gives the vector itself. So this 0 need not necessarily be 0 or 0, 0, all that. So it is that vector which when added with any other vector gives the same vector. So 0 plus V should be equal to V. That is what we want. And then the existence of additive inverse. So there is a vector V prime in V such that V plus V prime should be equal to 0. So you add V prime with V, you should get the 0 vector that is there in the vector space. Then you say that this V prime is the additive inverse of the vector V. So these are the 4 conditions that has to be satisfied with respect to the operation plus. And similarly, with respect to dot, there were 4 conditions. So with respect to dot, there were conditions that also spoke about what is the relationship between dot and plus. When both the operations are involved, what happens? So in this, the first condition was 1 times V. where 1 is the real number 1. When you multiply 1 with any vector, you should get the same vector. Then alpha times beta v should be equal to alpha beta v. So when you, here you're doing scalar multiplication in v, and then again you will get a vector as output. Again you're doing a scalar multiplication. Here you're multiplying two numbers first, and then that resulting number you're multiplying with the vector v. So there is a difference in what we are doing on the left hand side and the right hand side, but irrespective of what order we choose, we should get the same answer. And then the property over distribution of scalar multiplication over addition. These conditions should be satisfied, and the same for alpha plus beta v should be equal to alpha v plus beta v. So these are the set of conditions that has to be satisfied for all vectors in V and for all scalars. So even if for one vector, if any one of these conditions is not satisfied, then the set is not a vector space. So for a set with two operations to be a vector space, every single condition has to be satisfied. So to say something is not a vector space, it's enough if you just tell one of the conditions is not satisfied. Okay, so this was vector space. Is there any questions on what a vector space is, or how to check whether something is a vector space? Any questions on that? Yeah.
Hi ma'am, I wanted to ask, like, is there any quicker way to check that vector space? Is it there or not? It is not.
No, if to check something is a vector space, you have to go through all these steps. Means you have to check each and every condition. There is no shortcut to it. You have to check all the conditions, and only if all the conditions are satisfied, it is a vector space.
Okay.
Hello, ma'am.
Yeah.
Actually,
Yes.
unluckily, I was slightly late. Did I miss something important? Or
No. I just defined what a vector space is. That's it.
okay, ma'am. Okay, thank you.
So any questions? Any or shall we quickly take an example? Yeah. So we have a lot of examples. R with respect to the usual addition of real numbers and usual multiplication of real numbers. This is a vector space, and you can think of any Rn. Rn is the set of all n tuples. So this is the set of all x1, x2, etc., xn, where all xi's are real numbers. So the set of all n tuples, that's put together called Rn. So Rn with respect to the usual addition, and the usual addition in Rn is component-wise addition, and scalar multiplication again is component-wise. So all these are vector spaces. So mostly what we look at in the course is this, right? R2 or R3. These are the common vector spaces that we look at the course, or some subsets of these. Okay. So do you want any examples on vector spaces, or shall we proceed?
Ma'am, please go with a single example.
A single example, which is a tough one and covers all these points.
Yeah, it is not any of the usual ones.
Yeah.
So we will take this example. So this is a subset of R2, right? It has two components, means
Yes.
it's set of ordered pairs. So this is a subset of R2 where the first component is fixed. The first component is 1. There is so 1, 1, 1, 2, 1, half. All these are elements in this set. Half, 1 does not belong to this set. So if any element has to belong to this set, then the first component has to be 1. So now I'm going to define. So a vector space, I can talk about a set being a vector space or not based on the addition and scalar multiplication that is defined on it. Okay. So now suppose I define addition to be the usual addition, and dot to be the usual scalar multiplication. So So is this a vector space? Let's call this V. Is V comma plus comma dot a vector space?
No.
Okay, why not?
Because when we will add two vectors, if the other vector has like other than one or anything basically other than zero, then we will have something different in the x element x.
Yeah, exactly. So 1 comma 1 and 1 comma 2 belong to V, but when we add them, we get 2 comma 3. This does not belong to V, right?
Yes, ma'am.
Yeah. So the addition is not closed. Even scalar multiplication is not closed, but we are just interested in one of the properties being violated. So yeah, addition is not closed. This is not a vector space. So now I'm changing the definition of addition. How I'm going to add two vectors is 1 comma y1 plus 1 comma y2 is equal to 1 comma y1 plus y2. So here the addition is defined this way. So let's call this plus 1, means the subscript 1 refers to this different kind of addition. So this addition is equal to, the first coordinate doesn't get added up like the usual way. 1 is fixed, comma, y1 plus y2. This is the usual addition. And then I define scalar multiplication also similarly. Alpha times 1 comma y is equal to 1 comma alpha y. So here I am applying the scalar multiplication that is newly defined, dot 1. So now with respect to plus 1 and dot 1, is this a vector space?
Yes.
Yes.
Okay. How do we check?
Add any two vectors.
Yeah, we have to check all the properties. To say something is not a vector space, it is enough if we just say that one of the properties is not satisfied. But to say something is a vector space, you have to check all the properties and everything has to be satisfied. Only then we can tell that it is a vector space. Okay, so is it closed under addition? If I add two vectors, will the resultant also be in the vector space?
Yes, yes.
Yes.
Yeah, because the first coordinate is getting fixed, means the addition is defined in such a way that this one doesn't change to anything else. So this is
It's not a
always
vector
going to
space,
be,
ma'am.
huh? What is it?
Ma'am, it's not a vector space because 0, 0 does not satisfy there.
No. That's what I was telling. 0, 0 not necessarily means 0, comma 0. What you need to look for that vector v such that v plus
V plus 0 should be
equal to v.
equal
Now
to
I
V.
need to find what this 0 is. So v is going to look something like this.
Ma'am, it should be 1
v0.
comma 0.
Yeah, exactly.
Mm-hmm.
So this v is going to be 1 comma v1. So 1 comma v1 plus something. Let me put two components for it. Say x1 comma x2 should be equal to 1 comma v1. So what is 1 comma v1 plus this? First of all, the 0 has to be in the vector space, right?
Mm-hmm.
The 0 element has to be in the vector space. So from that condition, we know that this x1 has to be equal to 1, right?
Has to be equal to 1.
Yeah, because only then it will be in the vector space. So now when I add these two vectors, I should get this vector. So what should my x2 be?
0.
Yeah, because when I add these two vectors, what I'm going to get is 1 comma v1 plus x2. This should be equal to 1 comma v1. So when I equate these two components, I get x2 is equal to 0. So 1 comma 0 acts as the 0 vector. Right? It need not be equal to the usual 0 comma 0. That's what I was telling. there should be a vector which satisfies this. And this vector serves the purpose. So like this, can you check all the, yes.
One short question, ma'am. For checking the vector space, instead of taking general vectors, we can take some specific vectors which belong to vector space and check on them.
No. See, what does the axioms doesn't say for a particular V1, V2. This is for all V1, V2 in V. So you cannot choose vectors. You need to check for every possible vectors.
That
so
means we have to take the general vectors.
Yeah, okay, general. Yeah, you need to look at how a vector in the vector space is going to look like. So any general vector in this is going to look like 1, V. You cannot choose these particular vectors and then proceed. Instead, you should take general vectors like what we did here. Here, 1, V1. Yeah.
Got it.
So like this will be a vector space. You can check all the other axioms as well. We have already discussed this exact same vector space also. So this is a vector space. So yeah, the thing is here again, the 0 vector need not be equal to 0, 0. So you need to calculate the 0 vector based on the addition and dot scalar multiplication that is defined on the set. So a set alone cannot be a vector space. A set along with an addition and a scalar multiplication, only when you talk about both the operations, then you can tell that whether it is a vector space or not. And based on the operations, everything of the vector space is going to change. The structure itself is going to change just based on the operations plus and dot. Okay, so this is a vector space. What is a subspace? What is a subspace of a vector space?
It is a part of the same vector space, and it is also closed under addition and multiplication of its own.
Okay, so it is a subset of a vector space, which is a vector space in itself. So W is a vector, V is a vector space, and you're taking a subset of W, and W comma plus comma dot is a vector space. So a subset which is a vector space in itself means it is a subset, but yeah, it is also a vector space. So that is a subspace. It is a subspace. When you talk about subspaces, you're talking about the same plus and dot that is defined on V.
Ma'am, it doesn't need to satisfy all the properties of vector space, right?
It should, because it is a vector space, it should satisfy all the axioms, right?
Hello, ma'am.
Yeah.
Ma'am, subspace and vector basis are same.
No. Basis is something that is defined for every vector space. Subspace just means that this is a subset of a bigger vector space and it is a vector space in itself.
So every subspace is a vector space, right?
Yes.
Okay.
So again, to check that this is a vector space, you should make sure all the conditions are satisfied. But what is the advantage of talking about subspaces is that it is enough if you check just 2 conditions. Okay, 3 conditions. What are the 3 conditions?
Existence of 0. And
0.
It should be closed on addition and closed on multiplication.
Yeah.
As per the definition.
Yes.
Right. So you want 0 vector to be in the vector space. It should be closed under addition and closed under scalar multiplication. So if you just check these conditions, it is enough to check whether it is a subspace. This is an if and only if condition. It's a characterization for subspaces. Why needn't we look at the other conditions?
Because it is a subspace. It is a subset of that.
Yeah, it is a subset of the bigger vector space, and you can always treat the vectors in the subspace as vectors of the bigger space, and all these conditions are going to be satisfied there. So yeah, we just need to check this. 0 belongs to the vector space. Vector space is the subspace is closed under addition and it is closed under scalar multiplication, And once this happens, we can tell that it is a subspace.
Ma'am, I have a question.
Yeah.
When we're checking whether 0 belongs to or is contained in W, we've just seen that 0 need not be 0, 0. So if the vector space is not the usual addition and scalar multiplication, and therefore the 0 is not really 0, 0, maybe it's like, for example, 1, 0 in our previous case, then would that 1, 0 be checked, or would we have to check 0, 0 only?
No, the 0 of the vector space. So
Yeah,
this is a subspace of some other vector space. So the 0 of that vector space should belong to this subspace.
And not necessarily 0, 0.
Yeah. In this case, if you're looking at a subset of this vector space, you need to check if 1, 0 belongs to that subspace.
Okay.
As per the definition. As per the definition, you have to check that if it is 2, 0, then it does not belong to this space, right?
Yeah.
Suppose it is 2, 0, it is not belonging here. So it cannot be a 0.
Yeah. So now suppose you take W to be the set of all 1, y such that y not equal to 0. W is a subset of V, right? It's a subset of V. Right? No harm, right? I'm just removing one of the elements from V.
Yes, ma'am.
Hello, ma'am.
Yeah.
Ma'am, why it is needed to check the subspace as 0, 0 vector or others conditions? Because it is already a subset, no?
No. It is a subspace if and only if these conditions are satisfied. You needn't check C. First of all, for it to be a subspace, it should be a subset of.
I just try to say, ma'am, all subsets, if it is under V, the subspace, then the all vectors must be obey these rules, no?
No. So look at this set that I was talking about, W. It is a set of all 1, y, where y is not equal to 0. Is it a subset of V?
Yes.
Is it a subspace?
Yes.
No.
1,
This is
what?
not a subspace.
Y is not equal to 0 means no.
So I can take 1, 1 and 1, -1. These two belong to W, but when I add these two, it becomes 1, 0. This does not belong to W.
Does not belong.
Yeah.
Ma'am?
So, yeah.
Ma'am, I don't really understand the notation V plus and dot.
No, V is a set, plus is an addition that is defined on V, dot is a scalar multiplication that is defined on V. That's all.
Okay, so what is this notation exactly?
So can you define what a vector space is without knowing what the addition and scalar multiplication is?
No.
That's all. This is the addition that comes with V. This is the scalar multiplication that comes with V. That's all.
Okay.
Yeah.
So it can't be considered a vector of any source, right?
No. This is a space with addition defined as plus and multiplication defined as dot. That's what we put it together as V, plus, dot. That's all.
Okay. Thank you, ma'am.
And can I ask one question out of the way?
Yes.
Actually, the quiz there is hardly few days left, 2 or 3 days left. So what all important should be covered to cover all the topics at the earliest?
Everything is important. There is nothing that you can leave, because all these concepts are interrelated, and even if you don't know one of them, if you're stuck midway, you will not be able to proceed if you don't know that concept, right? So there is no use learning what is nullity and rank without knowing what is basis. So you might be able, if the question starts with some vector space is given, and then you're asked to find out the null space and basis for null space, and hence the nullity. You might know that nullity means the number of elements in the basis of the kernel. You might know the definition of kernel, but if you don't know how to find the basis, then you will not be able to solve the problem at all, right? So all these topics are important because everything leads to the next. And the problems are also going to be like that only. You already attempted the mock, right? So it's going to be similar to the mock.
Okay.
Yeah. Okay. So the concept of a vector space and a subspace is done. Now, next thing is what is a linear combination. So linear combination is something that we are already doing in a vector space. So what is a linear combination? What is a linear combination?
Every vector in the vector space can be represented as a linear combination of the bases.
No, linear combination just means that if you have a set of vectors,
Ma'am, a set of vectors
linear
are
combination means
multiplied
you're
by
allowed
scalars
to
and
you're
added
allowed to
together.
yeah, you're allowed to multiply with scalars and you're allowed to add. That's the only thing that you're allowed to do. You cannot multiply two vectors or anything like that. So what you're allowed to do is multiply with scalars and add. So this is a linear combination of these vectors. So the only operations that you're allowed to do is scalar multiplication and addition. So when you do that, you get a linear combination of a set of vectors. Okay. When do you say a set of vectors is linearly independent?
Ma'am, theoretically, if we add all vectors given in a vector space, given in a set of vector space, not all vectors, and any vector is not every vector is unique. What I mean is, if we combine two vectors, it is not producing any other vector. So if we have three vectors, the third vector is not produced by the combination of two vectors, or vice versa.
Yeah. So you
Actually,
take a set of
in above equation, if alpha 1 and alpha 2 all are 0, then they are linearly independent because we don't have any other way to get a 0 out of it.
Yeah.
Otherwise,
so you want to put a 0 here, right? Then you want all the alphas to be 0.
Yes. That is the only way we have.
Right. So yeah, as you all said, linearly independent means that no vector in this set can be written as a linear combination of the other vectors in this set. Then you say that this set is linearly independent. How do we put it down mathematically is, we write 0 as a linear combination of these vectors. Obviously, when alpha 1, alpha 2, alpha n, all these are zeros, this is going to satisfy, right? But if that is the only way it is possible.
Actually, it forms a homogeneous system of linear equations, and the solution we get is 0.
Should be unique. Yeah. So if a linear combination of these vectors, if you can write 0 as a linear combination using these set of vectors, and if that is possible only when all the coefficients are 0, then you say that the set is linearly independent. Or in other words, in simple language, no vector in this set can be written as a linear combination of other vectors in this set. Then you say that the set is linearly independent. Okay, yeah. So as you already mentioned, from here we get a homogeneous system of linear equations. And what are the variables there? What are the unknowns?
Alpha 1 and alpha 2.
Yeah, the coefficients. The coefficients are unknowns. So we try to solve a homogeneous system. And we know that the homogeneous system always has a solution. It either has a unique solution or it has infinitely many solutions. For the set to be linearly independent, we want a unique solution. Right? So if this system is a square system, so if I get a square matrix, then what is the condition that I want?
It should be invertible. The matrix we get should be invertible.
Determinant should not be 0.
Not equal to 0.
Yeah. If the determinant is not equal to 0, then we say that the system is, the set is linearly independent. So this is the case only when the coefficient matrix is a square matrix, because we can talk about determinants only for square matrices. Okay, what is linearly dependent?
Just a question, madam. When we write the coefficient matrix, we write them as columns or rows in this case?
No.
Doesn't
this
matter.
is going to, no. This is going to expand in some way, right? Like
actually, he is asking whether we write v1, v2 till vn as columns or rows. Actually, I prefer to write them as columns.
No.
Suppose v1 is say
okay,
a1.
fine.
Ma'am, it's a square matrix, so it won't make any difference because we have to find the determinant.
No. I think that was not the question. So the question was this: should we write the vectors as rows or columns? This is actually a system of linear equations, right? So when you have a system of linear equations, there is a particular way of writing the coefficient matrix, right?
Actually, this will be like Ax equals B, where B and A is nothing but alpha 1, alpha 2, alpha 3. We have to write it in row. And
No. A is not that. X is alpha 1, alpha 2. The unknowns are the X vector.
X is alpha 1, alpha 2, and
actually, the first column of the matrix is vector v1.
You'll get v1 here. Or wait, will we get v1 here? V1 has to be multiplied with alpha 1. So the coefficients of alpha 1 will be first column.
V1,
V2, Vn as columns.
Yes.
So you'll get it like this.
Actually, just try to form a system of the homogeneous system of equations as we have studied in week 2, 3.
Yeah. So if V1, V2, Vn and all are vectors in R3, you're going to have 3 components each. So you will get 3 cross n matrix. 3 rows and n columns.
Ma'am, so
just said it is a square matrix, madam.
No. If it is square, means if it is a
okay,
3
if it is
cross
square,
3
the
matrix.
determinant. Okay, sorry. Okay.
Yeah.
Ma'am, so the elements of V1 will be displayed as a column, V2 as a column, and so on, right?
Yeah. So it will be like this. Suppose V1, V2, Vn and all are in Rm, then it's going to be V11, V12, V13, V1m, whatever is the notation that we are giving. All the components of V1 will come in the first column.
Okay.
Ma'am, after solving the linear combination, if I get alpha 1 to alpha n all are 0, then I conclude that it is a linearly independent.
Yes. You want only 0 solution. You're not allowed to have any other solution.
All are 0
is the only,
all
0
are
is the only solution. Yeah.
And what about the determinant? I am out of.
No, determinant comes into picture when you have a square system. So you have Ax is equal to 0. This is a homogeneous system of linear equations, right?
Yes.
How many solutions does it have?
1.
2.
No, only 1 unique solution.
Unique solution.
That we need to check.
Yeah, you need to check that.
Unique solution and
it can either have a
infinity
unique solution or it can have infinitely many solutions. We know that 0 is always a solution. So we know one solution. No solution case is not possible. It can be the case that 0 is the only solution, or there are other solutions as well.
Okay,
so
we
now
should first check through determinant that determinant not equal to 0 means there is a solution.
Determinant not equal to 0 means there is a unique solution.
Okay.
Yeah. But if you cannot calculate determinant for rectangular matrices, right?
Yes.
Yeah. So the general concept is this homogeneous system should have a unique solution. If the coefficient matrix is square, then it's easy if I just check the determinant. Is it clear?
Yes,
No, confused. Yeah, I thought that you will discuss the theory with example.
Okay, we can do that. But this is week 3 content. You should have gone through it.
Yes, I already solved all the assignments, but now.
Okay, let's take these two vectors. So this is a subset of R3. I want to check whether this is linearly independent or not. Is it linearly independent?
Yes, ma'am, of course.
Yes.
Ma'am, can you tell, is it linearly independent?
Yes.
Why?
Because if I solve it, then I will get only one solution.
Actually, you don't need to solve it. See, one of the first vector is not the linear combination. Multiply first vector with something, you cannot get the second vector, right? Therefore, they form the independent set.
So if you have just a set of two vectors, it is very easy to check whether they are linearly independent or not. If one of the vectors is a scalar multiple of the other, then it is linearly dependent. If it is not a scalar multiple of the other vector, then it is linearly independent. But let's go by, so this set is linearly independent. Let's go by the usual thing. So what I have to do, I have to do alpha 1 into the first vector plus alpha 2 into the second vector is equal to the 0 vector. I want this to have a unique solution, that is alpha 1 and alpha 2 should be equal to 0. So what do I get? Alpha 1 plus alpha 2 is 0. Alpha 1 plus 2 alpha 2 is 0. And then 0 alpha 1 plus 3 alpha 2 is 0. So now I can write this in matrix form, right? AX is equal to B. 1, 1, 1, 2, 0, 3. Alpha 1, alpha 2 is equal to 0, 0, 0. Now you want to check whether this system has a unique solution or not. Can you calculate determinant?
Yeah, actually, this is what we have.
It is not square matrix, so we can't.
Yeah, you cannot calculate the determinant because this is not a square matrix. So you have to go by the traditional method. How will you check whether this has a unique solution or not?
Row reduce.
Row echelon form.
REF or RRE.
Row echelon form. So one thing
Taking transpose.
No, why do you want to take transpose?
I don't think ma'am transpose will help.
No. See, when you take transpose, you're disturbing the system. You're not allowed to do that. You're only allowed to do elementary row operations.
And from the equation, we are getting alpha 2 is equal to 0.
So yeah, you needn't do all this rocket science of row echelon form, reduced row echelon form. You don't need anything. You just solve the system of linear equations. From here, you are directly have alpha 2 is 0. Substitute it to the first equation. You get alpha 1 is equal to 0. And that is the only solution. So done. But yeah, let's revise the concept of row echelon form and all that. For that, you'll do this.
Madam, may I ask a question here? Shouldn't it be 1, 1, 0, 1, 2, 0, and 0, 0, 3? And alpha 1, alpha 2, alpha 3? Or
no, you have only two vectors, right? Then
sorry. Yeah, my mistake.
Okay. So when you want to check for solutions, what do? You first write down the augmented matrix.
Ma'am, we can simply substitute in this equations and we can do with that method.
Yeah. As simple as that. But why I'm doing this is so that we can recall augmented matrix and all that. Row echelon form and all that.
Okay, ma'am.
So what you do, you write down the coefficient matrix A and then you add the last column. You write down the augmented matrix. And then you do row operations and reduce it to row echelon form. So what do we do first? Is the pivot here fine?
Yes, it's already present.
Pivot has to be 1, it is already 1. Okay. Now I want to make all entries below the pivot 0. This entry is already 0, so no problem. 0, 3, 0. I want to make this entry 0. How will I do that?
So R2 minus
R1. R2 minus R1.
You replace R2 with R2 minus R1. So 1 minus 1, 2 minus 1, 0 minus 0. So when you have a homogeneous system, it doesn't matter whether you put this B or not, right? Because it's all going to be 0 times something 0. Everything is just involving 0. So the last column is always going to be 0 when you have a homogeneous system. So you can ignore that if you want. And then now, is this in row echelon form?
No.
Yes, ma'am. Yes.
Yes, ma'am. Yes.
It's not, right? This is a pivot. And below the pivot, you have a non-zero entry. That's not okay, right?
That's a free element, right, ma'am?
3 to 0.
You have to make this 3 to become 0, right?
R3 minus.
We have to do this until we can create more zeros in the matrix.
Yeah. Means below every pivot, you should have 0. Can you please mute if you're not talking to me? Yeah. So now this is in row echelon form, right?
Yes.
Yes, ma'am.
Yeah. So the number of pivots or the number of dependent variables, when you have a pivot, that is a dependent variable, right?
Yes.
Yes, ma'am.
Yes, ma'am.
Dependent variable is when you have a pivot. Columns containing pivots. And independent means no pivot. So here you have 2 pivots and there are only 2 variables. So this is going to give me a unique solution, right? All variables are dependent. In fact, this system reduces to alpha 1 plus alpha 2 is equal to 0, alpha 2 is equal to 0, right?
Yes.
Yeah.
One short question I'm confused actually. For deciding the dependent and independent, I know how to do that. But does the matrix always needs to be in reduced row echelon form?
No, you cannot talk about dependent and independent variables if it is not in row echelon form. It's not necessarily reduced. Row echelon form is enough. Yeah. Okay. As per the lectures, it has to be in reduced row echelon form. Yes. But yeah, even otherwise you can do that.
Ma'am, suppose we have 2 dependent variable and 1 independent variable, then it will be a linearly independent or linear dependent.
And can you explain it? Please state that once again, that it has to be in reduced row echelon form.
Yeah. The concept of dependent variable and independent variable comes into picture when you talk about RREF, not REF.
Okay. Now I got it.
Two concepts come into picture when you talk about RREF.
Okay. Got it.
Okay. Yeah. So if there were 2 dependent variables and 1 independent variable, what does it mean when a variable is independent?
That
you're allowed to choose any value, right?
Yeah.
Yes, there are infinitely many solutions.
In that case, there'll be infinitely many solutions, right? Because you're allowed to choose any value for that variable.
And so if number of
So in this
dependent
case, ma'am, we have
variables,
infinitely many solutions.
No, here we have unique solution. No, there are only 2 variables and we have 2 dependent variables.
yes, ma'am. So if number of dependent variables are equal to the variables equal to the unknown values, then we have unique solution. And if they are not equal to, and then we have infinite many solutions.
Yeah, infinitely or no solution based on the matrix. Here we have a homogeneous system, so definitely it will be infinitely many solutions.
Okay, ma'am.
Yeah.
Ma'am, but in the last row, we have all zeros, and I think some sir has told that in the last row, if there is all the zeros, then it is a infinity many solution.
No, that is the case when you have a square system.
Okay, I got it, ma'am.
Yeah, here you have only 2 variables, no?
Okay, ma'am.
So you obviously will have a third.
Yeah, if we had also in the second row all zeros, then it would be the infinity many solution.
Yeah.
Okay, thank you, ma'am.
Okay.
I have one doubt related to vector space. Can I ask, Usmita?
Yeah.
When we are trying to find the dimension of the vector space, for example, v equals to x comma y, x plus y equals to 0. When we want to find the dimension, do we take dependent or independent? I have confusion here.
We'll come to that. Actually, that dependent variable and this dependent variable is not the same. Here it's different and there it is different. So when we discuss dimension, I'll tell that. So we'll take that
fine.
example. Yeah.
Okay, thank you.
Okay, so is the concept of a linearly independent
ma'am.
set here? Yeah.
Hello, madam.
Yes.
Hello.
Yeah, I can hear you. Can you hear me?
Yeah, ma'am. Ma'am, in case of augmented matrix, we never consider last column as a independent or dependent. Ma'am.
No, the last column doesn't correspond to the variables. No, it is the right hand vector. No, so why should that relate to dependent or independent variables? This
Okay.
doesn't correspond to the variables, right? This is the right hand vector.
Okay. Okay.
The first column of the coefficient matrix corresponds to the first variable. Second column corresponds to the second variable. That's it.
Okay.
Yeah.
Ma'am, suppose it is not a homogeneous system. Suppose it is formed like x plus b. So in that case, last column we consider like suppose we want to reduce row echelon form, then
no, even then dependent and independent variables comes from the A part, not from the B part.
Okay, it's come from only A part. Okay.
Yeah, because when I talk about variables, the coefficients of variables come from A, not from B.
Okay. Okay, madam.
Okay, so is the concept of a linearly independent set clear?
Yes.
Madam,
Okay. So
we're
then,
talking about so far unique and infinite solutions, right?
Yeah, yeah.
And no solution option is something which we can check with any of these procedures, or that comes with a different set.
Here this is always a homogeneous system, no? It's always AX is equal to 0. So this has a unique solution or infinitely many solutions. No solution is not possible because X is equal to 0 is always a solution.
Okay. And the unique solution would be everything being 0, alpha 1, alpha 2. Okay.
Okay, so when is a set linearly dependent?
Ma'am, when not all the coefficients are equal to 0.
Yeah, as simple as saying that when the set is not linearly independent, it is linearly dependent. So since the concept of linear independence is clear, you just need to check whether it is linearly independent or not. If it is not, then it is linearly dependent. So in terms of the coefficient matrix and all that, everything will just become the opposite. So here I don't want the determinant to be 0, whereas for linearly dependent, I want the determinant to be equal to 0. So in that case, AX is equal to 0 will have infinitely many solutions. So when there are infinitely many solutions, there will be non-zero coefficients satisfying this equation, right?
Yes, ma'am.
Yeah.
Madam, if unique solution is going to be only the case where all the alphas are 0, then why don't we actually declare it as such? Why are we actually?
No, we know that X is equal to 0 is always a solution. If it is a unique solution, then that is the only solution. So X is equal to 0 will be the only solution.
Okay.
Yeah. Okay. Next is the concept of span. What is span of a set? What is span of a set?
Remember, span of a set?
All the vectors in the vector space.
Is the different vectors it could produce with the combination
It is
of
a
different vector space.
Right. Different linear combinations.
Yes.
So this is nothing but set of all finite linear combinations.
And it must be independent set.
That
No,
would
not
be basis.
necessarily. No, span is different.
Yes.
That is basis. When you want them to be linearly independent as well, that is a basis.
Oh, yes.
Yeah. So when you want to take span of a set, you're generating all possible vectors by using linear combination. Means you're multiplying with scalars, adding and all that, and then you're generating as many vectors as possible That is called span of a set. And the span of a set is a subspace. It's a subspace of V, where V is the set from where we took these vectors, V1, V2, Vn. The span of a set is always a subspace. And when do you say a set spans a vector space? S spans V if span of S is V. That's it. A set is set to span a vector space if span of this set is equal to
enter V.
Yes. Yeah. So is this clear? When do you say a set spans a vector space? You just take the set of all possible linear combinations. If that is going to give you the entire space V, then we are done.
Okay, ma'am.
Can you firstly recap, ma'am?
Yeah. So I'll give
Here,
an
madam.
example.
Here, madam, a span is a set, no, madam. A span is a set, but how
Span
it is a
of a
subset?
set. But how?
Yes,
Yeah. The span
yeah.
of a set is a subset. I agree. It is a subset. You can
Yeah.
actually show that it is closed under addition, scalar multiplication, and the zero vector belongs to the span and all that. Can you quickly tell me how the zero vector belongs to the span?
Because it starts from 0, 0.
You can put all coefficients to be zero, right?
Yeah.
0 times V1 is equal to 0. This belongs to the span, right? Because this is a linear combination.
Yes, ma'am.
Yeah. So like that, you can check that it is closed under addition and closed under scalar multiplication. So the span of any set is a subspace.
Okay, so by definition, we have a zero element.
Yeah, means you can generate the zero element using these vectors, right?
Right.
Yeah, means you just multiply any vector with 0.
What I mean to say is when we defined subspace should have a zero element is what we were actually defining it as a primary one, right?
Yeah.
Therefore, my question, when I say span, automatically it has a zero element.
Yeah. How it has a zero element is like how we generated 0 times V1. So span of a subset is not a subspace by definition. In fact, it is a subspace. You can prove that it is a subspace. Definition means you define it to be like that. But here we can actually prove that it is a subspace.
Okay.
Ma'am, just for clarity, we are saying the span of this spanning set is a subspace of V, but then we only say that it spans V if the span itself is giving the whole vector space.
Yeah.
Not just a subspace.
Yeah, this is right. Whatever you said now is right. The span is always a subspace, but if that subspace is equal to the entire vector space, then you say that the set spans the vector space.
Thank you.
Okay, so now let's take an example.
This is because every subset is every set is a subset of itself, right? So when that is why when the span S spans V, hit the span.
So span S is always a subset of V because it is always a subspace. It is set to span V when the other way happens, when every element of V can be written as a linear combination of elements of S. This is always true. When this happens, you say that S spans V.
Okay, got it.
Yeah.
But span will always have fewer elements. Okay, there is a combination.
Span is going to have infinitely many elements, right? Span of any set.
Yes, but they all are contained in the. They are all contained in V, correct?
Yeah, because V is a vector space.
There's no way a span can be more than a V because that way it's going to be some of the elements are going to be left out. So that cannot happen, correct?
Yeah, vector space is like The vector space is the biggest, and we are all these are inside it.
Okay. Okay.
And just one doubt.
Huh.
If we have a vector space which is Rn, and if the spanning set has more than n elements in it, then it will automatically span entire V, right?
No. If I take R2 instead of Rn, I'm taking R2. Now I consider this. What is the span of this set?
It will be X6, or basically same element, basically scalar multiples of.
It's going to be this line, right? Y is equal to X.
Yes.
This is not R2, right? This has more than 2 elements.
Yes, okay. Got it.
Yeah. So is it clear that the span of this set is this line?
Yes, madam.
Yes.
Yeah.
So what is span of 1, 1 and 1, 2?
R2.
A span of R2.
Yeah. 1, 1 is here. 1, 2 is going to be somewhere here. If I have two linearly independent vectors in R2, then they are going to span the entire space. So when I take all possible linear combinations, I'm going to get the entire space. So span of this set is R2. And how did I just look at the picture and say they are linearly independent?
Because both the vectors can be scaled.
They are on different
They can be
lines.
scaled. And any
They are
point can be
Different multiple.
any point can
if
be.
they are,
I mean, they are on different lines.
They are only intersecting.
Means they intersect only at 0.
Yes, there is only 0.
So if I take any two vectors here, then it is linearly dependent because one is a scalar multiple of the other. When I have vectors which are scalar multiples of one another, they are going to lie on the same line, right?
Yes.
So yeah. So one thing we know is okay. Let's define what a basis is. What is a basis?
It is the minimum spanning set or maximal linearly independent
set.
Yeah, it is a spanning set which is also linearly independent. Right?
Yes.
Or equivalently, it will be a maximal linearly independent set or a minimal spanning set.
Ma'am, like we said, that basis we know is a spanning set. Like for R2, it's 0, 1, 0, and 0, 1. But like above, how could you say that 1, 1, 1, 2 means just looking at the picture that it spans the whole R2? It's
so you know that if they have two elements, and I can get R2, right?
Yes, ma'am.
It is the
and it is not lying on the same line, right? So I'm going to I'll be able to generate the entire space. If I have two vectors lying on the same line, any linear combination is again going to lie on the same line. It's not going to go out of this line. But here they are not on the same line. Right?
Ma'am, it is the minimum number of vectors required to span the whole vector space.
Yeah, for R2 it is 2, yes.
Ma'am, but
because
for
it's
higher
true.
dimensions?
Sorry to interrupt. It is true because they are both linearly independent and R2 requires two vectors. That is the reason? Or
Yes.
Ma'am, but the definition that it is the minimum number of linearly independent spanning set is true for even higher dimensions, right?
Yes. Yes.
So it is safe to say that the minimum number of vectors required to span the whole vector space, if any vector is removed, it cannot span the whole vector space, even in the higher dimensions of R3 to Rn.
Anything.
Yes, ma'am. It is the
not
definition.
just Rn, in fact, any abstract vector spaces which we cannot think of in terms of Rn also, it is the same concept. Yeah.
Okay, ma'am.
So it is the maximal linearly independent set. That is, if you add even one vector more to the set, it's not going to remain linearly independent. Or it is a minimal spanning set. If you remove even one vector from the set, it's not going to span the set, span the vector space, then it is a basis. So it is like, in some sense, we are looking for the smallest set which is going to do all the job for us. So it's a spanning set which is also linearly independent. That is a basis. And any two bases, you can generate infinitely many bases for a vector space, and any two bases will have the same number of elements, and that number is called the dimension. So the cardinality of any basis, the number of elements in any basis, is called the dimension of the vector space. So are things clear till this?
Yes.
Yes, ma'am.
Okay. So now let's take the example. X comma y such that x plus y is equal to 0. So this is what ma'am was talking about. Is this a subspace?
Yes, ma'am.
Yeah, this is a subset of R2. This is nothing but the line y is equal to minus x. And we know that any line passing through the origin is a subspace in R2, right?
Yes, ma'am.
Yeah, so this is a subspace. Now let's find a basis for this subspace. So geometrically, we know that it is a line. So what is the dimension?
1.
Yeah,
1.
lines are one dimensional. You just need one vector to generate this entire line. So how am I going to find a basis for this set? I just need one vector.
Y is equal to minus x from this equation. So
1 0 1 0.
one is minus x.
Yes.
No, 1 0 does not lie here.
X comma minus x.
Minus minus
1
minus
minus 1.
1 1.
1
Yeah,
minus
yeah,
1
yeah.
or 2 minus 2.
Yeah,
Or
anything
minus
of that.
1 1.
Anything. So you just want x comma minus x. You can put any value for x. So let's take 1 comma minus 1. So this is a basis for this vector space. And this vector 1 comma minus 1 generates this entire line. If I have just one non-zero vector, it's going to be linearly independent naturally, right?
Can you repeat,
What do you
ma'am?
mean?
Any non-zero vector, if I have a set with just one non-zero vector, it is
This
linearly independent.
This I got like this example, ma'am.
You want me to explain this example? Okay.
Yes, ma'am.
So you have this subspace. It is the set of all vectors x comma y such that x plus y is equal to 0. What is this subspace? It's this line, right? You agree?
It is a line.
It is a set of all vectors satisfying y is equal to minus x. So it is the points on this line. Now you want to find a basis for this set. Now this set is nothing but x comma minus x. Y is equal to minus x and x varies. So I put any value for x, I'm going to get a basis, right?
Yes, ma'am.
Yeah.
Ma'am, here I have a confusion. According to definition of basis, spanning set, it should be spanning set and linearly independent.
Yeah.
But in this question, it is not a linearly independent because
why not?
Because the scalar multiplication
There is no other vector as there, so it is independent set.
If you have a set with just one vector where v is not equal to 0, it's always linearly independent, right?
Yes.
Singleton set. Singleton.
Singleton set need not any check for independent or.
Okay.
What should you do? Alpha times v should be equal to 0. But v is not equal to 0. This has to mean that alpha is 0, right?
Equal to 0, yes, ma'am.
So it is linearly independent.
Independent.
Okay.
Sorry to interrupt, Susmita. Here only I have doubt whether we are taking dimension as dependent variables or independent variables.
Yeah,
Count.
I was coming to that. Okay.
Yeah.
So now, when I have this set, this is the set which I can also write like this. Now, how many free variables do I have here?
One.
One.
Only one.
Yeah.
X.
Yeah. Once I fix a value for x, y is fixed, right? So y is dependent on x. So if I look at this version of the set, there is only one independent variable. So this independent variable has nothing to do with that. Like if you look at this as a system of linear equations, so it's going to be like what? 1, 1, x, y, 0. So now this is a pivot. This is actually the dependent variable, right? Because this is the pivot.
Yes.
Yeah. But here we are saying x is independent. So this independence and this independence is not related. I am telling x is independent because I am free to choose any value for x. You could have also written it like this. Y comma minus y. No harm, right?
Yes. No problem.
In this case, this is the independent variable here.
Yes.
Yeah, so it's not related to that. The independence that we talk about there and the independent variable that we talk here are not the same.
So here we are counting the free variables.
Ma'am, we will write minus. And we will write minus y comma y, no?
Anything, no? Same, no? Y comma minus y can also be written as minus y comma y. Because I'm just multiplying with minus 1, right? It's going to give me the same set. Span of x comma minus x is equal to span of minus x comma x. Right?
Yeah, okay, ma'am. Then the basis 1 comma minus 1 and minus 1 comma 1 is same.
This is also a basis. Right? This is going to be the vector here. It's still going to generate the same line.
Okay.
Oh, 1 comma minus 1 will be here, and this one will be minus 1 comma 1. It's all going to generate the same line. So this is a basis, this is a basis.
Ma'am, will it hold true when we take it into R3 vector space also?
Yeah, same, no? We'll take the same. So x comma y comma z such that x plus y is equal to 0. Okay, so what is x plus y is equal to 0 in R3?
Z is equal to 0.
Plane, madam.
It's a plane, right? So what will happen here? It is the set of all x comma minus x comma z, where x and z belong to R. Means you are not able to eliminate this z with the given conditions, right?
Yeah. Okay.
So z is also a free variable. So what is the dimension here?
Two. Yes.
Dimension is 2 because you are allowed to choose x and z. Means once you choose x, your vectors are not going to be fixed. So just choosing x is not enough. So if I choose x, I'm not getting that minimal spanning set. Right? So I need to choose the z component also. So the dimension is 2. And how do we find the basis?
Put x is equal to 1, z is equal to 0.
Put x is equal to 1.
And first put x equal to 1 and z equal to 0. Then put x equal to 0 and z equal to 1.
Yeah. So this is
Madam,
going to be a base.
Here independent variable are 2. So we can say that independent variable define dimension.
Yeah, but this independent variables is not that independent variables for system of linear equations. Not this. Yeah.
Okay.
Okay, so how can we write this? We can write this set as span of, okay, before span of, I can write it as x times 1 comma minus 1 comma 0 plus z times 0 comma 0 comma 1 such that x and z vary. So you just pick these two vectors. The set is already written as span of these two vectors, right? That's why I'm able to write it as x times this plus z times this.
Yes, sir.
Yeah. And it is also linearly independent, these two vectors. So it forms a basis.
Yes.
Actually, ma'am, this is the basis of subspace of R3, right?
Yeah, this is the subspace, the plane. This is the subspace of R3. So is it clear how we found the basis?
Yes, ma'am.
Yes, madam.
Okay. So vector space, whenever we have a vector space, we can associate a number with it, and that number is the dimension of the vector space. And the dimension is nothing but the number of elements in any basis of the vector space. So all this we have seen. Next, we have another concept of rank. Rank of a matrix. Let's get back to matrices. What is rank of a matrix?
All that
Number of
non-zero
rows.
number of column. Sorry, number of row with
non-zero rows.
Number of
Not
independent rows.
Number of independent
Number of
Yes, yes.
dependent variable.
By row space and column space.
Number of linearly independent columns.
variable.
Columns.
Or number of dependent variable.
Okay,
Can
so
we
this
say
is the
that,
number of linearly independent columns. And then when you talk about REF or RREF, then you talk about independent and dependent variables.
Okay. Okay.
And it is equal to number of linearly independent rows also.
Yeah, it will be equivalent to number of linearly independent rows also. So after you convert to REF or RREF, you check the number of non-zero rows.
Means number of dependent variable, no matter.
Yeah,
non-zero.
this is also equal to number of dependent variables. Now we are getting back to the old dependent variables, what we spoke about in the system of equation. Yeah.
So independent column means what, madam?
Linearly independent columns. So you take the columns and then you check whether the set is linearly independent or not.
Okay. All column like.
Madam, what is the difference
definition?
between?
But we have always been doing this. Yeah, what is the difference between what?
When we say row rank and column rank, are they two different things, and how are they
No,
different?
the row rank is equal to the column rank.
Row rank is equal to the column rank.
Yeah.
So why am I actually going for columns then? Any specific reason why I'm calling it number of independent columns of A?
No, we always deal with columns. That is why this is also equal to number of linearly independent rows. This will be equal to the number of linearly independent rows. We always deal with columns because when I talk about system of linear equations, the variables correspond to columns, right? So it's nice to talk about columns.
So alpha ones of every equation is what I'm referring to.
Yeah, no, this is also equal to the number of linearly independent rows. For the definition, we chose the columns. That's it.
Even I have a same confusion.
What I mean to ask is, like, when we wrote AX is equal to B, X is alpha 1, alpha 2 till alpha n.
Okay.
And A is the coefficient matrix.
Yeah.
So what I am talking about as a column vector is not the complete vector itself, but the first variable of all the vectors that are there.
No, when I have a matrix. Now I have a matrix. Let's not talk about AX is equal to B or anything. So I have some matrix.
Okay.
4, 5, 6, 7, 8, 9. When I want to talk about the number of linearly independent columns, what I will do is I will take each column as a vector. Now I have a set of 3 vectors. Now I know whether to check, I know to check whether it is linearly independent or not, right?
Yes.
That's what we are doing. That is actually the definition of rank of a matrix.
Okay. Then now
So
when
if
we
I
actually
have this, how many, what is the rank of this matrix?
2.
You will get 2 by doing this. You do all these operations and then you will get 2. But you can actually directly look at the matrix and tell because this is a scalar multiple of this.
Yes.
Yeah. So you can eliminate this off. Now, are these 2 scalar multiples of each other? No.
No.
These 2 vectors are linearly
Unique vector.
independent. So the number of linearly independent columns is 2.
Okay, that is what we call it as column rank of the matrix, is it?
Yeah, yeah.
But
And the column rank of the matrix is equal to the row rank. So now if we look at the rows, look at the rows now. 1, 4, 2, 3, 6, 6. Okay, nothing is directly a linear combination, but you can write this as a linear combination of the other 2. So,
ma'am,
yeah.
Here we actually segregated the rows of columns of the matrix into separate vectors. So can we actually do that? It's because a matrix is a separate vector or just a combination?
No, each row can be treated as a vector. Each column can be treated as a vector, right?
Yes, ma'am.
Ma'am, can we say when once we reduce it to RREF, then every column that contains the what you call pivot item is an independent column?
Yeah, if you have a pivot that's going to correspond to, you cannot say independent column, but that's going to correspond to a vector which is linearly independent. Means, so once I do RREF here, what do I get? 1, 4, 2, 2 minus 2, 5 minus 8, 4 minus 4. And then 3 minus 3, 6 minus 12, 6 minus 6. And then I can make this 1 and this 0. So this is after I do RREF, I have a pivot here, I have a pivot here, which means that the first column and the second column are linearly independent. And since there is no pivot here, it is dependent on the other 2 columns.
Yes, so that means that the matrix, the same columns corresponding are independent.
Yeah.
No, actually, first and second column is dependent.
No, first and third column is dependent. 1, 2, 3, 4, 5, 6. They are not dependent. No, they are not scalar multiples of each other. We'll check the row dependence also. So alpha times 1, 4, 2 plus beta times 2, 5, 4 is equal to 3, 6, 6. Alpha plus 2 beta is 3. 4 alpha plus 5 beta is 6. 2 alpha plus 4 beta is 6. Okay, this is a redundant equation because this is 2 times this. Now let's solve this. 4 alpha plus 8 beta is 12. 4 alpha plus 5 beta is 6. Minus 3 beta is 6. Beta is 2. If beta is 2, this is 4 minus 1. Alpha is minus 1. So minus 1 times the first row plus 2 times the second row gives the third row. So you're seeing that if the columns are linearly independent, the rows are also going to be linearly independent.
Ma'am, here we have two completely contrasting things. When we were looking at dependent and independent variables earlier, we were saying the ones which had the variables which had the pivot element were actually dependent variables, and the other one would be the independent. And over here, the columns which have the pivot element are considered as the linearly independent columns, and the third one is considered as dependent. Am I right?
That's because we were talking about independent variables there.
And here it
we
is
are
about columns.
Yeah, we are not even considering any system. You understand why when we have a pivot, it's called dependent. So say we have this, or let's say this is 0, x1, x2, x3, and then say some b1, b2, this is 0, this is also 0. So why do I say when there is a pivot, it is dependent?
Value is dependent on another variable.
So x1 plus 2x2 plus 3x3 is equal to b1. x2 plus 4x3 is equal to b2. So from here I can tell what x2 is. b2 minus 4x3, and then I substitute, and then I'll tell what x1 is. So x2 is dependent on x3. So it is a dependent variable. And once I plug in those values here, x1 is dependent on this x2 and x3, or only
x3.
Yeah. So here when we're considering only variables, then we can consider the ones with the pivot element as actually dependent and the other one as independent. But when we're talking about checking rank, we're talking about the linear independence of columns, and the columns with the pivot element would be considered as linearly independent.
Yeah, the columns where you get the pivot, that set forms a linearly independent set.
Okay, thank you, ma'am.
But there's not, it means this is the definition of rank, but REF and RREF comes to our rescue. So just do this. Find the row echelon form and then find the number of non-zero rows. That's it. That's the rank of a matrix.
Easier way.
Yeah. So this is rank. And what is nullity? Null space.
Rank minus number of elements. Sorry, n.
Yeah. Okay.
Rank
what is
minus
null
n.
space?
X is equal to 0.
Yeah. Set of all solutions of AX is equal to 0. You have a matrix. You just take the homogeneous system and then find all possible solutions for this. That's the null space.
Madam, in that sense, can we say null space actually is populated by independent variables?
Yeah, right. In fact, that's how you get a basis for the null space, right? You choose all those independent variables and then you get a basis.
Okay, I mean, like I forgot about that. Sorry, but I was just looking at your earlier definition that you gave about number of dependent variables. That's the reason why I was just relating it.
Right. So for rank, it is number of dependent variables, and we already know rank. Okay, what is nullity? Let's go sequentially. What is nullity?
Number of independent variables.
Yeah, dimension of null space, right? This null space is a vector space. This is a subspace. The dimension of this null space is nullity, or as you said, number of independent variables. Yeah. So number of rank plus nullity will be equal to the number of variables. Right?
Yes, sir. Yes, ma'am.
And this is also equal to number of columns of A.
And we can also say n minus rank.
Yeah. Rank plus nullity is number of columns of A. Right?
Yes.
That is why columns are nice. That's why we talk about columns everywhere. Even though rows also play the same thing here, we still talk about columns because of this.
Because
Columns are
columns number
special.
is a variable.
Dimension
That
of
was
null space means the dimensions of basis of null space.
Dimension of null space means number of elements in basis of null space. Yeah.
That was my earlier question, madam. When we are writing column vectors, but when we say column vector, we are writing x, y, and z. But in the case of this, when we are talking about them as variables, they are not x, y, and z, but in fact the coefficients of the x terms, all of them in a column. Correct?
Ma'am,
when you write it down as a system of linear equations, then that's how it turns out to be. The coefficients of the first variable comes in the first column. The coefficients of the second variable.
Number of columns of A is number of vectors.
Yeah. Okay. Yes.
Number of variables in a vector, isn't it? It's not the vectors itself.
No, you mean this, right? Alpha 1 v1 plus alpha n vn.
Yes.
Correct.
That way you mean the number of vectors, right? Yeah.
Yes.
Yeah.
In the domain.
Ma'am, can we actually? I actually get confused about null space. So can we actually hit a little example so I can just get through it?
So now let's take a matrix 1, 2. We'll do that 1, 2, 3, 4, 5, 6. 2, 3, 6. So we already know rank is 2, right? For this matrix. Oh, not 2, 3, 6, 2, 4, 6. This one and this one. These two columns are linearly dependent and these two columns are linearly independent. So the rank is 2. We already did REF and then we got number of non-zero rows to be 2, right?
Yes.
Yeah. So now let's find the null space. Null space means what am I going to do? I'm going to find, I want to find solutions of this. So to find out solutions of this, I will consider the augmented matrix and then convert this into a simpler system and then find the solution. But because this is a homogeneous system, I can ignore this portion, right?
Yes.
Yeah. So now do the usual row echelon form. 1, 4, 2, 2 minus 2, 5 minus 8, 4 minus 4, 3 minus 3, 6 minus 12, 6 minus 6. And then 1, 0, 0, 4, 2, 1, 0, 0, 0, right? I'll make this 1 first and then I will do plus 6 times this. Yeah. So now my reduced system is this. x1, x2, x3 is equal to 0, 0, 0. So I am going to find all those x1, x2, x3 which satisfies this. x1 plus 4, x2 plus 2, x3 is 0. x2 is 0. And the third equation doesn't give me any information. So x2 is 0, which means this reduces to x1 plus 2, x3 is equal to 0. That is, x1 is equal to minus 2x. So what are the solutions?
Minus 2x.
Minus 2x3,
0x.
0, and x3.
Yeah. x3 varies over R. Means there is no restriction on x3. Because the third row is completely 0, I am not getting, or in fact, there is a pivot here, there is a pivot here. x3 is an independent variable because there is no pivot in the third column, right?
Yes, ma'am.
Yeah. So can you give a basis?
-2, 0, 1.
Yes, -2,
-1, 0,
0,
1.
1.
Yeah,
Yes,
that's
fine.
all. This is the basis for null space.
Could you please tell the dimension of this?
Dimension is 1, no? Because there is only one free variable. x2 is fixed, x1 depends on x3. There is only one free variable, which is x3.
Okay.
And dimension is number of free variable or cardinality of basis?
Cardinality of basis, but when you talk about the dimension of null space, it becomes the number of free variables. But basis means dimension is the cardinality of a basis.
Madam, but this process is exactly the same as what we did earlier, isn't it?
Yeah, right.
Rank is 2 here, and nullity is 1.
Yeah.
So dimension
because
is
there are 3 variables, right?
Yeah. So will the dimension be 3?
Dimension of what is 3?
Rank plus nullity gives us dimension, no?
No, dimension, okay. You're talking about dimension of the domain space, right? That comes into picture when we talk about linear transformation. For now, rank plus nullity is number of columns of A.
Okay. Okay, so this is not the dimension of A.
No. There is no concept of dimension of a matrix. We only have dimension of a vector space.
Okay.
Actually, I have doubt when x or y is 0. Here x2 is 0, right? That's what I have little doubt.
So what is the doubt? x2 is 0. So what happens?
Whether we have to count it as a free variable or...
No, it's not free, no? x2 is 0. It's not free. You're not allowed to choose x2. x2 is already fixed.
Okay.
Madam, then the difference between the two processes is we work with the augmented matrix, or we don't work with the augmented matrix. Is that the way I have to say it?
No, both are the same, right? You don't need this. You don't need this portion.
Yeah. So
you
once
do the
I
row
write
echelon form to the matrix and then solve the reduced system. That's it.
Yeah. If I have to find the rank of this matrix, it is 2, isn't it?
Yes, rank. You do the same thing here. You get the rank, and then you do this matrix multiplication. You get null space. Both can be done just by doing the row echelon form.
Okay. Basis for the vector space is going to be, the subspace is going to be what in this case, madam?
Here we found the subspace. This is the null space of A.
Correct.
And we found a basis here.
Correct. But this is the basis for the null space. When we are talking in the earlier, when we were working on the earlier problem, we wrote the same thing and we actually said it is basis for the subspace itself, isn't it?
Yeah, because we were considering a subspace there. Here we were considering the null space, which is also a subspace.
So both are the same? No, can't be, right?
No, null space is a special kind of a subspace, that's all. See, even this subspace can be thought of as a null space, right?
Can we tell the null space by just looking at the RREF?
1 second, I just write this down. So this is the matrix A, and this subspace is nothing but the null space of this matrix, right?
Yeah.
So
I'm telling that
110 is possible because we have minus x.
1 minus 1, sorry. 1 minus 1 and 0.
No, I'm writing this equation as a matrix.
Equation. Okay.
So this is what? X plus y is equal to 0.
I got, ma'am. I got that.
Okay, so the null space is nothing, that is also a subspace. It is a special kind of a subspace because we know that we want to find out the solutions of AX is equal to 0. That's all.
So null space is a subset of the domain. And the domain can have its own basis, correct?
No, there is no concept of domain codomain here because we are still in the matrix form. Domain codomain comes into picture when we talk about linear transformation. Right?
So null space is defined as AX is equal to 0.
Yeah, the set of all solutions of AX is equal to 0. That's all.
But that's a homogeneous system, isn't it?
Yeah.
So any homogeneous system is a null space actually?
No, like, yeah, null space of what? Means the homogeneous, if you have a homogeneous system, you are actually finding the null space of that matrix, right? If I have any AX is equal to 0, if I'm trying to find the solutions X such that AX is equal to 0, I'm actually finding the null space of the coefficient matrix, right?
Okay. That was more a question for me because I was not able to link this earlier, sorry. So,
okay.
Ma'am, if the null space only comprises of the 0, 0 vector, then what will be the nullity?
0 means, what is nullity? Dimension of basis. So if this is my vector space, what is a basis for this vector space?
Would it be itself?
No, there is no basis, no, because this, if you have a 0 vector, the set cannot be linearly independent, right?
Is origin.
So for a basis, it has to be linearly independent also. Yeah. So by
So it does
default,
not have a basis.
the dimension of the 0 space is defined to be 0.
Okay.
So the nullity will be 0 in this case.
So we can tell that for a homogeneous system of equation which has unique solution, then nullity is 0.
Yeah. Why so?
Because rank is nothing but
if I have unique solution, how many dependent variables do I have?
0.
No. Unique solution.
Oh, unique solution.
All will be dependent.
All are the dependent.
So rank is taking up all the variables. It means like this is equal to rank, right? Dependent variables is rank. So because of this, nullity will be 0.
Then the
nullity
rank will be the
space.
dimension.
So nullity is 0 in the sense only 0 vector, correct?
Null space becomes the 0 vector. So yeah, nullity equal to 0 if and only if the null space is the 0 space. And this means AX is equal to 0 has a unique solution.
So we will face problem when we have infinitely many solutions, which is means.
So if it has infinitely many solutions, the null space definitely has a non-zero vector, and the nullity is definitely greater than 0.
Greater than 0.
Is at least 1.
If we consider a matrix of 3 cross 2, what will be the maximum rank of it, ma'am? Rank and maximum nullity. Can it be rank plus nullity will be 2, according to me.
3 cross
2. Yes.
Right.
So if you ask me what is the maximum rank, means can it be 2?
It can be, right? So the rank has to be less than or equal to the minimum of number of rows and columns. Because what is rank? It is the number of linearly independent rows. Number of linearly independent columns.
Yes.
So the number of linearly independent columns cannot be more than the number of columns, right?
And the nullity will be 0 over here.
If rank is 2. Yeah, in this case, rank is 2. So nullity will be 0. But if it was this.
Can you repeat that statement? Minimum of rows or columns?
The rank can be at most minimum of number of rows and columns.
So if it is 2 by 3, for example, here it is 3 by 2, one more rectangular matrix if we take 2 by 3. So again the 2 maximum.
Rank can be maximum.
Because row rank equal to column rank.
Yeah.
That's why it is a minimum.
Yeah. Because rank is equal to number of linearly independent columns.
So in 3 by 2 matrix, maximum is 2. So
yeah, and row rank is number of rows, linearly independent rows, and we know these two are equal.
This is equal.
If there are no, if simply the question is asked without giving any matrix, and they can simply ask the matrix order is 3 cross 2. So the answer will be the same, ma'am?
Yeah, the rank can be at most 2. If it's 3 cross 4, the rank can be at most 3.
4.
3. Minimum number.
Minimum number.
Sorry, ma'am. Can you repeat that?
Normally, we take in m into n. We always take the number of columns as the n variable.
Even I had the
rank plus nullity equal to n, no?
Yeah.
So then it will be 4.
No. Rank plus nullity will be 4, but rank can be at most 3.
Okay.
So the nullity has to be at least 1. At least.
So at most minimum of m and n, is it? Can we treat it as that?
Yes.
Yeah.
Show an example regarding this 3 into 4.
Yeah, so the rank can be at most 3, right? Because it has to be less than or equal to minimum of number of rows and columns.
There will be 4 columns over here.
Yeah.
3 rows.
Yeah.
And 4 variables also.
Yeah.
Can't it be maximum? I'm not able to understand this part.
No. See, what is rank? By the definition
okay,
that I gave.
I understood, ma'am. I understood. Yeah, I understood. Yeah. Thank you.
The number of linearly independent rows or number of linearly independent columns. You have only 3 rows. You cannot have more linearly independent rows.
We cannot get more pivot elements.
Yeah. So even without knowing the matrix, we know that there is a non-zero vector in the null space. Right?
Yes.
That's why the nullity is greater than or equal to 1.
Actually, I have in the mock, when I solved the first question 3 cross 2, they asked the same question. And then when I given rank, the maximum rank will be 2. I got it wrong.
Okay.
Madam, just to clarify this thing, when we say a rank is actually representing the number of independent rows and dependent variables, is it?
In the mock, they are asking for the minimum value of rank. So maximum rank is. So
you mean to say that the rank of matrix is minimum of the rows or columns, whichever is minimum. Maximum rank can be that only.
Yeah.
Okay.
So rank can never be minimum 0?
Yeah, I'll tell you. So what is the maximum rank possible?
Can you please explain it with taking the example? Like take a matrix 3 plus 2 and then take 2 cross 3.
Rank possible for number of column.
Let's not take examples because here we are dealing with general matrices, right? So let's look at all the possibilities.
2 rank will be 2, but nullity will be 1.
That is what I meant. Take a 3 cross 2 and then take a 2 cross 3, and please then explain it with this.
Okay, fine. Okay. So I have a 3 cross 2 matrix. So the maximum rank is 2. So the possible ranks are 0, 1, 2, right?
Yes.
But A is not a 0 matrix. So the rank cannot be 0, right? Okay. What is rank plus nullity?
2. This is 2. This will be 2.
Rank plus nullity should be equal to 2. So if rank
Equal
is
to
0,
n1.
nullity is 2. If rank is 1, nullity is 1. If rank is 2, nullity is 0.
Actually,
so this is not possible. So this is not possible.
It will be better if you write the same thing A 3 by 2 and below if you write m by n. Then rank plus nullity equals n. So n is nothing but 2.
I got in rank can be 0, 1 and 2. And 0 rank is not possible because the matrix is not 0. I got till this point. How have you related the nullity with it? I know rank plus nullity would be equal to the number of columns in matrix A. Can you explain
So
me?
0 plus what will give me 2? 2. 1 plus what will give me 2? 1.
1.
2 plus what will give me 2? 0.
Okay, ma'am. Got it. Now
So the minimum rank is this.
Rank should be always minimum.
Okay. Minimum rank is this. Then the maximum, then nullity has to be 1.
Should be 1.
And when we say the matrix is non-zero, what if matrix is made of all ones? 1, 1, 1, 1, 1, 1, like that?
Even that case rank is 1, no?
It won't
will still remain
1.
After you do row echelon form, you'll get this. See, when you have a non-zero entry, even if everything else is 0, when you have a non-zero entry, that column is anyway going to be linearly independent, right?
Yes.
Okay, that is right.
Ma'am, I have a question. Can I?
Yeah. Oh, 1 second. Before the question, shall we do this? 2 cross 3. So in this case, what is the maximum possible rank?
3.
No.
2.
Suppose this is non-zero. So this case is ruled out. What is nullity? What are the possible values for nullity? Rank plus nullity is 3 here. 3.
At least 1.
Yeah. So minimum nullity is 1. Maximum nullity is 2. You just write down all possibilities, you will know the answer.
Yes, ma'am. Thank you.
Yeah. So someone had a doubt.
Yes, ma'am. I'm clear about it. Thank you, ma'am.
And if it's not mentioned that the matrix is non-zero, then we will not eliminate that one.
Yeah, this will not be there. Means that will still be a contender.
Okay.
Yeah.
And just to going back to the definitions, rank is the number of dependent variables or number of linearly independent rows, is it?
Yeah, columns, rows, dependent variables, yeah.
Number of dependent variables or non-zero rows being linearly independent rows. Is that the way to be actually read?
No, see, what is dependent variable? Dependent variable, independent variable all comes into picture only when we talk about RREF, not otherwise. Randomly, a variable cannot be dependent or independent. So this concept of independent and dependent variables comes into picture when we do this RREF.
Right.
In RREF or REF, the number of non-zero rows will tell the rank of the matrix. The number of dependent variables will tell the rank of the matrix.
Okay, so linear independence of the rows is not does not actually play a role.
That is the definition. This is a way of calculating.
Okay. Okay.
Okay, so digested all this. So what do? We stop or proceed?
Ma'am, these notes will be uploaded, right?
Yeah, I will do it as soon as the session is over.
Excuse me, ma'am.
Okay, thank you.
Yeah.
Ma'am, in the second revision session, can we discuss mock quiz too? Means
Yeah, we
specific
can.
questions that are hard to solve.
Are you going to take the second revision?
Mostly, if I'm not busy, I will only take.
And please
I want to take because it will be a continuation of
Yes,
today's
ma'am.
session.
Yes, ma'am.
Ma'am.
It would be
We thought
better
that
to.
Srikanth sir will take.
No, Srikanth is in Maths 1, no?
Oh,
Shubham, you mean?
sorry, he is in stats. Sorry, my mistake.
Shubham
He is
sir
in stats too.
Shubham sir would take it.
Oh, yeah, Srikanth is in Stats 2 also, yeah.
Excuse me, ma'am. No, one more question regarding the sixth question.
Sixth, okay.
Okay, here, when we take the statement 2, why it's wrong?
A is the matrix representation of T with respect to. I think everything is correct. Statement 2 is right.
The answer is written as 4.
No, the number of correct statements is 4.
I read it wrong.
And would you be discussing the linear transformations today?
If we can. If it's not too much for you, we can continue.
Yes, ma'am. Please continue.
Yeah, we can continue, ma'am.
Because we have discussed only 1 week till now.
Yes.
Oh, yeah.
Finally.
Week 8 we will not discuss, okay, because that's pretty simple, right? It's just the Gram-Schmidt process.
Oh, yes, ma'am. You explained it already very well in few sessions back.
Yeah, so maybe you can watch that in case you have doubts.
Yes.
Ma'am, a small rough discussion.
Kindly discuss some linear transformation. So
yeah, linear transformation.
Yeah.
Just a rough discussion, not too deep. Yeah.
No, I am jobless. Means I can go on till 12, 1 o'clock.
If only if you have time.
So
Yes, ma'am,
we
we
will
can do all
stop
night.
when you feel it's too much. Okay.
And also affine subspaces, can you say?
We will do linear transformation and then get there.
Okay, thank you.
Actually, one small thing. There is one thing. Whenever we have a non-trivial or a solution, it must have infinitely many solutions. This means what actually? What can you explain us with some?
Okay. So you have Ax is equal to 0. You have a non-zero solution. There is an x which is not equal to 0 satisfying this, right?
Okay.
And then what about alpha x? Is alpha x 0? X is non-zero.
So
Alpha is any number.
Yeah, alpha x is not 0. Okay.
What is A times alpha x?
This is alpha A times x. Yes.
Yeah.
Alpha is just
I know
a scalar.
x is already a solution to this system. Alpha times 0, so 0.
Yes.
Right? X is already a solution.
Yes.
So can you see that when there is one non-zero solution, there are infinitely many non-zero solutions?
Yes.
How is that, madam?
No, when x is not equal to 0 is a solution. I have produced alpha x, which is also a solution, right? A times alpha x.
Alpha can be any
alpha
value.
x.
Okay.
Alpha
Okay.
can
Okay.
be multiplication. Okay. Okay. That's what it means.
And the reason is that this is a linear algebra, right? Everything goes from one point to another in a linear way. There is a linear relationship. That is why we can put alpha anywhere, right?
Yeah. Okay.
Ma'am, in linear transformation, can you discuss the basis of the range? That part is a little confusing.
Yeah. We'll do that. Okay. So what is a linear transformation? We use the variable t from V to W.
from one vector space to other vector space.
Ah.
T of V1 plus V2 equal to T of V1
Yeah.
plus V.
Having two condition hold.
And C alpha V.
So a linear transformation is a function between two vector spaces satisfying these two conditions. It's a special kind of a function, that's all. So if you want to check something is a linear transformation or not, you need to check if it satisfies these two conditions. When you say a linear transformation is an isomorphism.
Then T of V equal to W.
And T
is 1, 1 and on 2.
Bijective. Yeah, it is bijective.
Isomorphism means, yeah, bijective. So it is both 1 to 1 and on 2. When do you say a linear transformation is 1 to 1?
T of 0.
T of 0 equal to 0.
T of
F of S
V.
equals
V equal to 0.
That equal only if V equal to 0.
Yeah. So T of V is equal to 0 implies V is equal to 0. That's all you should check. So whenever you're asked to check whether a linear transformation is 1 to 1, you just have to do this. And for on to?
T of V equal to W.
For every W in the codomain, there exists a V in the domain such that, yeah. So there is a pre-image for every vector in the codomain. Let's take an example. Say T from R3 to R3, T of x comma y comma z is equal to x plus 1 comma y comma z y. Is this a linear transformation?
No.
Okay, why not?
Because when we are adding plus 1, so that would create a different equation when we'll be equating it individually.
So it is not a 1-1.
It is
No. Forget 1, 1. My question is this a linear transformation?
No,
it is because of zy.
No, 0 is not there.
It is because of that plus 1.
Z into
Okay, it's because of plus 1 and zy.
Degree 2.
You're not allowed to multiply because we are dealing with linear stuff, and you're also not allowed to add stuff like this. So if it is a linear transformation, T of 0 should be 0. What is T of 0 here? 0 is the 0 vector.
X, Y, Z will be 0, then it should be 0.
So this is not satisfied. T of 0 is not equal to 0. So you're not allowed to do this plus 1. Now, what happens in the ZY case? T of 0 is 0 here. What is the problem then?
ZY.
ZY2.
No. Where is the problem?
The degree of the equation will change. It has to be a linear, so the degree has to be 1. Here the degree will change.
No. As simple as that. To check whether it is a linear transformation, check these two conditions. So what is T of, say, alpha V, alpha x, y, z? So this has to be T of alpha x, comma, alpha y, comma, alpha z. So that is alpha x, alpha y, alpha squared zy, right?
Yes.
This is not equal to alpha times x, comma, y, comma, zy. Yeah. So you're not allowed to have this multiplication as well. Okay, so let's ignore all this. Let's take a linear transformation.
But ma'am, we can have like x plus y, right?
X plus y is not a problem. You're not allowed to add constants because this will be disturbed. And you're not allowed to multiply variables because these two conditions will be disturbed.
Okay, ma'am.
Okay, so let's put x plus y. Now, is this 1 to 1? How do we check that?
It is a one-to-one, ma'am.
We have to do this. T of x comma y comma z is equal to 0 comma 0 comma 0 implies x comma y comma z is equal to 0 0 0. This is what I want to prove. Put it aside. Let's start here. What is T of x comma y comma z?
X, Y, X plus.
Yeah. What does this say?
Is equal to 0, y equal to 0.
Yeah. Does this imply this?
Yes. It's 1, 1.
No, right? What happens to z?
Z will also be 0.
Z will also be 0.
No, why? This doesn't say z has to be 0, right? What is image of 0 comma 0 comma 1?
X plus y equal to 1. So it won't satisfy.
So 0 can
this
be
is not
any
1, right?
arbitrary value because its value doesn't.
Z can be anything. So this is not 1
0 0 Z is the 0 vector.
No, any vector with z component non-zero you take, and then you're going to get 0, right?
Yes, correct.
0 0 1, 0 0 half.
Yes,
0
any
0
scalar.
100. Yeah, take any number.
Okay, got it.
Yeah.
Is
this on to?
Ma'am, not getting 1 to 1. P x y z equal to 0 0 0 implies x y z equal to 0 0 0.
This is what we want to prove.
Actually, 1 to 1 is quite easy. On to.
Okay, let's do on to. What do we do for our on to? For every x comma, or let's take a comma b comma c. A, b, c in R3. We want x, y, z in R3 such that T of x comma y comma z is equal to a, b, c, right? This is what we want, right?
Right.
Yes.
Okay. So I want x comma y comma x plus y to be equal to ABC.
Yes.
That is x is equal to A, y is equal to B, x plus y is equal to C. What is x plus y from these two?
A plus B is
So whenever I pick a C which is not equal to A plus B, I won't have a pre-image, right?
right.
Say 1 comma 1 comma 3. There is no pre-image for this. Or you can just put it, in this case it is very simple, but otherwise you can put it as a system of linear equations. 1, 0, 0, 0, 1, 0, 1, 1, 0, x, y, z is equal to a, b, c. So 1, 0, 0, 0, 1, 0, 1, 1, 0, a, b, c. You want a solution for this for all a, b, c. So do the row echelon form. 0, 1, 0, 0, 0, 0. After doing row echelon form, you will get this. And then you will get this. Okay, I think I should do it. 1 minus 1. 0, 1, 0, C minus A.
Yes, ma'am, it would be C minus A minus
B.
B.
Okay.
Yes, ma'am.
0, 0, 0. A, B, C minus A minus B. So this will have a solution only when this is 0, right? Because there's a 0 row here.
Yes.
So C minus A minus B should be 0. That is, C should be equal to A plus B.
Yes.
But I can find vectors such that this is not satisfied. So this is not on.
So, ma'am, can we say that anytime when some x, y, or z is dependent on other, then it is not onto?
No.
We have to find only one vector which will not satisfy the condition. That is enough to prove
Yeah.
that this is not correct.
Yeah.
Ma'am, can
So
you
let's
please
take the
explain
same.
why is it not 1-to-1?
It's
Ma'am,
not
this
1-to-1.
explanation actually, I wasn't able to understand completely what onto was mean for linear transformation in this example. Please, can you brief it?
Okay, I'll do both. So 1-to-1, I want to prove this. Whenever a vector is taken to 0 by the linear transformation, the vector has to be 0, right? So I do the same thing. T of a vector in the domain x comma y comma z is equal to the 0 of the codomain, which is 0, 0, 0. So here when we don't mention anything, we are always considering vector spaces with respect to usual addition and subtract, scalar multiplication. Yeah, so it will always be the 0 vector. So yeah, is equal to 0, 0, 0 implies x comma y comma z is equal to 0, 0, 0. This is what I want to prove. So I start with this. If I somehow get this, then it is 1-to-1. So what is T of x comma y comma z?
As per definition, it is x comma y comma x plus 1.
Yeah, that is equal to 0, 0, 0. That's what we have started with. So when I put this, what do I get? I get x is equal to y is equal to 0, right?
Yes, ma'am.
I don't get this, right? To get this, I want z also to be equal to 0.
Okay, we cannot say anything about z.
Yeah. So can you find a vector, non-zero vector, which goes to 0?
Yes, ma'am. Say it is 1, 2, and 3.
No, 1, 2, and 3 will go to 1, 2, and 3. 1, 2, 3 actually goes to 1, 2, 3.
Okay, by chance it is. Yes, ma'am.
0, 0, 3. Where does 0, 0, 3 go?
It
0,
doesn't
0, 0.
Yeah. So there is a non-zero vector which goes to the 0 vector. So it is not 1-to-1.
Okay, you mean to say that 0 should be unique, right? In the transformation, we are getting 0, 0, 0 from 0, 0, 0 and also from 0, 0, 3. So two vectors are going to 0.
The pre-image of 0 should be only 0.
0 should be unique. No? Right.
Yeah.
So if we
The
can
pre-images of 0 should be unique.
Yes, ma'am. Yeah. Got it.
Yeah.
So if we can prove that 0 is unique, then
And
the
it
vector
should
will
give
be
the
1-to-1.
image of 0, 0, 0.
Yes.
Yeah, we already know this. For a linear transformation, we already know T of 0 is 0. So you should tell that there is no other vector that goes to 0.
Okay, ma'am.
Yeah, somebody
But
was asking
just,
something.
yes, just proving that 0 vector is unique, is it sufficient to prove that it is 1-to-1?
No, we are not proving 0 vector is unique. We are proving that the pre-images of 0 is
Are
just the
unique.
0 vector.
So if we can prove that, then it is a 1-to-1 transformation.
Yeah, yeah. Okay. For onto, what do we want to prove for onto? For every vector in the codomain, we want to find a vector in the domain that satisfies this. That is, we want to find a pre-image for every vector in the codomain. So for every vector in the codomain, we want to find a vector in the domain. This is codomain.
Yeah.
R3 in the codomain, and this is the R3 in domain, such that this is satisfied.
Actually, at first we establish the image first, then search that
Yeah.
where is the
Yeah.
pre-image exists
You,
or not.
yeah, you pick a random element in the codomain and check whether a pre-image exists or not.
Yes, yes.
Yeah. And then you write down what is T of x comma y comma z. So now you have a system of linear equations, right? You just want to see if you can always solve it. That's what
How
we did
we
here.
created this matrix?
So what is the system we have here? X is equal to A, Y is equal to B, X plus Y is equal to C.
Yes, ma'am.
My variables are X, Y, and Z, right?
Yes, ma'am.
So the matrix is, what is this equation? 1, 0, 0, X, Y, Z is equal to A.
Oh, okay, ma'am. I got it, ma'am.
Yeah.
So, ma'am, basically, if we can prove that one of the variable like C or A or B is dependent on other two or anything, then it will automatically be not onto, right?
No, we'll do the same example with different space. Same transformation. Now, is this one-to-one?
It is not one.
Yes,
T
it is
of
one
x
to one.
comma y.
Yes.
I want
There is
this implies x comma y is equal to 0, 0. This is what I want. I have x comma y comma x plus y is equal to 0, 0, 0. So this is one-to-one, right?
Yes, ma'am.
This implies x is equal to 0, y is equal to 0. That's what I want. So this is one-to-one.
And actually, I applied the chain because it is going from R2 to R3. It is always one to one.
No, not necessarily. I'll give you a next example where that's not satisfied.
It may be one-to-one, but we cannot guarantee that it is one-to-one.
Yeah. But can you tell that it cannot be onto?
Yeah, it's never onto.
Yes, no.
Yeah. You have, like, in some sense, more vectors here,
Yeah.
right? Yeah.
More vectors that is not mapping through the pre-images.
So for every A comma B comma C in R3, we want
A pre-image.
x comma y in R2 such that T of x comma y is A, B, C. The same previous thing will work, right? Same reasoning.
Yes, yes, ma'am.
X plus y should be equal to A, B, C. So you want C to be equal to B plus A.
Correct, yes.
Yeah.
So if C is not equal to B plus A, then there is no pre-image, so it is not
right. Let's take the same example from R3 to R2 as T of x comma y comma z say is equal to x comma x plus y. Can this be one-to-one?
No.
No.
It's not be one-to-one because Z's are.
Here you have a bigger space. So there is no way I'm going to send just one vector to 0. I need to send more vectors. So T of x comma y comma z is equal to, or even if I was going to involve z, even if I was going to involve all the variables, it's still not going to be 1, 1 because I cannot put all this. Means obviously I want to send every vector here to some vector here. Only then it is a function, right? So there is no way I'm just going to send 1, 0 to this 0 and then send everything everywhere else.
Ma'am, if you write y comma x plus z, Then if I put x equal to 0, y equal to 0, and z equal to 0, then it makes 0, 0 also.
Yeah, t of 0 is always 0. The question is the other way around.
Oh, that's it.
We can have x as 2 and z as -2 and we will still get
Yeah,
0,
that's
0.
it. 1, 0, -1. I'll still get 0, 0.
Yes, yes.
So it's not 1 to 1. But is it on to?
No.
I want p of x comma y comma z to be equal to a comma b. So y comma x plus z is equal to a comma b. So y is equal to a, x plus z is equal to b. This I can always solve, right?
Yes, ma'am.
For any b, choose some thing. Like you can even choose x is equal to 0 and z is equal to b, right?
Yes, ma'am.
A comma b will always have a pre-image like this. 0, a, b.
Now here, how you made y comma x plus z equals a comma b?
No, on to. I didn't write down the details completely. For every a comma b in R2, I want to find an x. Is it clear?
Yes.
Yeah. So in fact, a comma b has two pre-images, at least two pre-images. B, A, 0, 0, A, B. At least two pre-images, right? I can give one more pre-image, B by 2, A, B by 2. All these are going to go to A comma B, right? I just want to solve this system, right? 1, 0, 1, B, 0, 1, 0, A. This is already in row echelon form. How many solutions will the system have?
Infinite.
Yeah, because there are only two pivots, two dependent variables, but there are three variables, right? So there is one independent variable, so infinitely many solutions. That's why we are having multiple pre-images. I'll give one more, b by 4, 0, not 0, a, 3b by 4. Like this for any two, means x plus z should be equal to b. I can produce infinitely many such values, right?
Ma'am, can we conclude if the transformation is from a higher dimension to a low dimension, it can never be one-to-one?
Higher dimension? Yeah, yes. There is a tutorial video that I had made on all this. Maybe you can watch that. From Rn to Rm in general, what are the different possibilities and all that I had explained there.
Okay.
Okay, so is 1, 1 on to clear? How we check and all
Madam,
that?
on the previous problem, can you just say it once again, please?
Yeah. This one or the previous one?
Previous one, madam.
Okay. Everywhere it is the same concept. T of v is equal to 0 implies v is equal to 0. This is what you want to prove.
Yeah, that part was clear.
Yeah, so you just write down T of v is equal to 0. V means v belongs to R2 here.
Correct.
So T of x comma y is equal to 0. The 0 of R3, 0, 0, 0. What is T of x comma y? This.
Yeah.
X comma y comma x plus 1.
It gives 0.
If this is equal to 0, then I get x is equal to 0, y is equal to 0. And that's all I want, right?
Yeah, and it is 1 on 1 or 1 to 1.
Yeah.
On to, madam. The on to part was the one.
For every element in the codomain,
Correct.
You want a pre-image satisfying this. Yeah, you want a pre-image.
Yes.
So T of x comma y is equal to ABC. So x comma x plus y should be ABC.
So C is always equal to A plus B. Okay.
Yeah.
But it isn't. Okay. Got it, sir. Yeah. Thank you. Thank you.
Is the second example, is it onto that because it has infinite number of solutions?
Yeah, this is onto, no? You can always produce a pre-image.
Because it has infinite number of solutions.
Means I have produced solutions. ABC is random. So I have produced infinitely many pre-images for a single A.
Whenever there is a free variable, we can assume like that.
Yeah, but I have written it down as a system of linear equations and it has infinitely many solutions. So this system has infinitely many solutions, which means going back, there is always x comma y comma z satisfying this.
Ma'am, how A comma B written as BA0?
Where? Here.
A comma B. Yeah.
I just want y is equal to a is fixed. So everywhere y is equal to a. The other condition says x plus z should be b. B plus 0 is b. 0 plus b is b. B by 2 plus b by 2 is b. B by 4 plus 3b by 4 is b. Like that.
So, ma'am, whenever the question, type of question is coming, so when we say R3, we linear transformation from R3 to R2, so it is not one, but it is onto.
No, it may be onto, it may not be onto. What if I put 0 here? It's not onto, right?
Yeah.
It's not on to one or on to, ma'am? On one.
It can never be 1, 1. Because this is bigger than this.
Because of the high dimension to low dimension. That means, ma'am, we should to check in pre-image there should be in domain there should be one unique vector and that give us a 0, 0 vector in domain in range, no, ma'am?
Yeah. Pre-images of 0 vector should be unique.
Should be unique. Or in onto case pre-image multiple.
Every vector should have a pre-image.
Or it may be multiple numbers of pre-image.
Yeah. Like here, multiple pre-images.
Multiple pre-images.
Ma'am, I have a question here. Okay, I remember sir once telling, like Shubham sir once telling in one of the sessions, like the transformation T is 1 to 1 if and only if the nullity of the transformation is 0.
Yeah.
And it is onto if and only if the rank of the transformation is equal to the dimension of the codomain. So in that case, can we also represent transformation in matrix form and reduce it to row echelon and check nullity and rank? Will that also work to conclude on 1 to 1 and on?
Yes.
Okay. Thank
So
you.
we haven't done that yet. Okay. So what is kernel of a linear transformation? This is similar to null space of a matrix, right? Am I audible?
Yes.
Yes, ma'am.
Yeah. So the kernel of a linear transformation is similar to null space of a matrix. So it is a set of all vectors such that T of V is equal to 0. So what happens if the transformation is 1 to 1? What is this set?
homogeneous system.
No, if T is 1 to 1, what do we know about this set? If T is 1 to 1, what do we know?
Ma'am, that there is only one vector whose value is 0.
Yeah. If it is 1 to 1, we know this. TV is equal to 0 implies V is equal to 0. Which means this set is 0.
If it is 1 1, then the unit vector should be 0 0.
Yeah. And what is nullity? This is a subspace.
Is dimension of kernel.
Dimension of kernel. So if and only if nullity is 0, right?
Because 0 0 vector contain nullity is 0.
Kernel of T is the 0 subspace, so nullity has to be 0. What is range of T or image of T?
So basically nullity of T is equals to number of vectors which is inside the kernel of linear transformation.
Not number of vectors, number of elements in the basis, because there will be infinitely many. If there is one, there will be infinitely many. Yeah.
Okay, ma'am.
So what is the range of a linear transformation? Range of any function, no? It is the set of all
solutions.
It's the set of all TV. That's all. Images. W is equal to TV. V belongs to V. So it's the set of all images. This is a subspace of what?
Codomain.
Because we are in the codomain. TV. We have taken the image. Now what is rank?
Dimension of image.
Yeah. Dimension of the image space. So what happens when T is on 2?
Image equals to the codomain W.
Yeah. Image equal to codomain. And when does this happen? Rank is equal to dimension of codomain. So this and this. And again we have rank nullity dimension theorem. Rank of T plus nullity of T is dimension of domain.
Vector space V.
Yeah, this is the domain. So now let's go back. First example was from R3 to R3. We have already shown it is not 1 to 1. If it is not 1 to 1, what can we tell about the nullity?
It cannot be
Not 0.
Not 0.
It is not 0. So it is at least 1. So what can we tell about the rank?
Sorry, ma'am. What's up?
What can we tell about the rank?
It would be 3.
It would be less than 3.
Maximum.
It cannot be 3.
It has to be lesser than
Maximum 2.
It can be maximum 2. So if you have from same dimension spaces, if it is not 1 to 1, it cannot be on 2. Is it clear?
No, ma'am.
So what do I have? T from Rn to Rn is not 1 1. Then nullity is greater than or equal to 1, right? If it is not 1 to 1. This implies rank has to be less than or equal to n minus 1. Because when you add both, you should get n, right? This implies not on. So if you have the same dimension, it is not 1 to 1, if and only if it is not on to. Both are the same. When both are different, we have seen all possible combinations.
I'm not able to understand.
What are you not able to understand?
Here, if it is not 1 to 1, then the nullity will be 0.
No, no. If it is 1 to 1, nullity will be 0.
Minimum 1, if not 1 to 1.
If it's not 1 to 1, it is not equal to 0, so it is at least 1.
It is not 1 to 1.
So, ma'am, when the transformation is from Rn to Rn, it's enough to check only one condition. If it is not satisfied, definitely the other will not be.
Yeah. Okay. Only for same dimension spaces. Otherwise, everything is possible. Yep.
No, you give this type of question. Rn to Rn, that will be.
This is done in a product of finite spaces. In a product. Yeah, so this kind of questions you should be very careful because it's comprehension. No, you have to. If you go wrong in one step, everything after that is going to be wrong. Okay, I guess you should try this on your own and then we can. Okay. So, do we stop? Continue?
Ma'am, do we have
One
a
question
solution
on this.
for this mock?
Can we continue?
Has the solution been uploaded?
Well, mock solution, I don't remember. I think I.
Yeah, it is. Yeah, it is
uploaded.
It is there. Mock for this solution.
And can we continue for some time?
Yeah, okay. I don't have a problem. Okay.
Can we do affine subspaces?
Okay, for affine subspaces, I think we need a little more.
Actually, affine subspace, is it possible tomorrow freshly we can?
Ma'am, I think we can stop here because whatever we have covered today, we'll revise it and we will come back in the next session so that it is not much to revise it so that we have to come with the doubts also.
Actually, next session we will not keep it on
But
Friday.
I don't think that in next session we will able to cover all the 2 weeks.
That's why. That's why we will have it.
Yeah, that's why.
No, that's why we will have it tomorrow also, on Friday also. Okay, if she is okay.
No, we have only on Friday. We have one more
I
session
hope-
on Friday.
Yeah. There is only one.
Can we have it tomorrow also?
Actually, we had planned 2 sessions for quiz 2 because we wanted to cover 1 to 4 also. We were actually planning only one session, 5 to 8 revision.
Yeah.
Ma'am, tomorrow we also have statistics.
Subspace requires a lot of attention. That's why. Yes.
Okay, maybe you can go through all this content. On Friday, do you have stat 2 session at 8 o'clock?
Yeah.
Or can we prepone it to tomorrow so that we can have some extended session? The Friday session, can we prepone it to tomorrow if it is agreeable to all?
No, sir. Let it
We have a Python session.
Let it be one
I
day.
guess having a break is good because you will get time to revise before Friday's session.
Yeah,
Yes,
correct.
yes,
Correct.
actually able to
Because
create
we
some
need
good doubts.
some homework.
Ma'am, so today we have covered till 6th week, right? Week 6.
Yeah, we haven't done matrix of a linear transformation. Other than that, everything of week 6 is also done.
Okay. So we are
And in
only
week
have
7, we
matrix.
don't want to do inner product and norm and all that, right? So
Only there is 3 weeks of pendings now.
No, we have only equivalent matrices.
Ma'am, in a way, we can say 2.5 weeks are pending still.
On the last 3 weeks or 2.5
Only
weeks.
1 week is pending, right?
Yeah.
Week 7.
Yeah.
Okay,
Yeah,
Week 8
because
is
we are
easy
not going
and
to do week 8, I guess.
week
Yeah,
7 we have to cover.
Ma'am, but there is still some doubt in week 8.
Yeah, you can ask doubts, no problem at all.
Yeah, that's why I'm asking that
Ma'am, by
whoever will be
revising,
comfortable, they can ask, and whoever will be not comfortable, they can leave and they can
Yeah, yeah.
watch the recording later.
Yeah.
Yeah.
ma'am, for our quiz 2, should we be focusing more, like we have already been doing all the 8 weeks, but then can we expect 5 to 8 week, 8 week will be given more stress on
Quiz
the
2 will be like
weightage?
mock quiz 2.
Okay.
Yeah.
So we can see a replica of that in the quiz 2. Mock one.
Yeah. No, not like exactly, but yeah, more or less like
Some
this.
idea here.
Yeah.
Okay. Thank you, ma'am.
Ma'am, if we revise all the graded assignments and mock test question paper, I expect that the questions come in the quiz 2 is related, that is similar type of question will come.
Yeah, if you revise all these assignments, it means that you are revising all the concepts of weeks 1 to 8. So definitely you will get 100 in quiz 2.
Madam, sorry to break the conversation, but can we go over this last one again, madam? I heard the explanation. Somehow I'm not following. Yeah, the last sentence that you have written over there.
Okay.
Yeah, this, yeah.
So we know that if a linear transformation is 1 to 1,
yes,
then its kernel is 0, the 0 space.
Correct.
So nullity has to be 0.
Yes, nullity is 0. Yes.
So if it is not 1 to 1, nullity is not 0.
Yes.
That's what I've written here. So P is not 1 to 1. So the nullity is at least 1.
Yeah.
And I have the same dimension, means n and n.
Yeah.
So if nullity is at least 1, rank plus nullity is equal to n.
N. Okay, got it. Okay.
So if this is
n less
if
than
nullity is at least 1, so this maximum it can take is n minus 1.
Yeah, yeah.
Ma'am,
So
how
if
it is nullity is at least 1, ma'am? Can you show?
Because it is not 1 to 1.
Oh.
Here we see, no, if it is 1 to 1, then nullity is 0. So if it is not 1 to 1, nullity is not 0. If it is not 1 to 1, what does it mean? There is at least one non-zero vector which goes to 0, right? So which means this kernel becomes a subspace of
if it is 1 1, then there should be at least one 0 vector is there.
The 0 vector will always be there because the 0 vector goes to the 0 vector. Are there more vectors? That is the question.
Oh, if it is satisfied 1 to 1, then we can say there is at least there is must be unique 0 vector is there.
Means the pre-images of 0 is just the 0 vector.
Yes, just the 0 vector. Okay.
Yeah.
Madam, and this holds only
and
when
if it is not 1 1, then and then maybe there is a multiple 0 vector in the pre-image.
No, not multiple 0 vectors. There are multiple vectors going to the 0 vector.
Oh, there's a multiple. Yes.
Yeah.
There is a multiple. Maybe there is a multiple.
There is a unique 0 vector only.
Yes.
So there is only one 0 vector here. There is only one 0 vector here.
If
and I know the 0 vector always goes here.
Yes. If it's 1 1, then it is possible. Then there must be one 0 vector in pre-image. Otherwise,
if it is 1 to 1, then this is the only vector that goes to the 0 vector.
Yes.
If it is not 1 to 1, there are multiple vectors going to the 0.
Goes to 0 vector. And this vector may not be 0 at least. Because 0 vector is a unique.
Yeah, it has to be some other vector, no?
And this will not hold once the R, if it is R power Rm and Rn, it will not hold, is it?
Yeah, this doesn't hold there because we have seen, no? One is one to one, not one to, and all that. This is not one to one, but it is on to.
Correct. Yeah.
This is one to one, but not on to.
Yeah.
Can you take one example and explain one more time, if possible, for on to?
Yeah.
Because on to, it's clear that the codomain should have three image. All the codomain should have three image.
Okay, maybe we quickly take the matrix and then move on. Or we have the transformation.
Actually, can you restate this mark 2 questions without giving answers again? Because I didn't attempt it.
We had kept it open for 4 days actually.
No, I know, but that was on weekdays, you know.
Actually, we gave it well ahead so that you know what you understand, don't understand, and then study accordingly. We can open it; it is not a problem. But
no, if possible, if you don't have any much administrative thing, you can reset it so that.
Yeah, I'll ask.
Okay, thank you.
Okay, so this is the linear transformation, matrix of the linear transformation we haven't done, so let's not do that part. Okay, so now what is the kernel?
That's nothing but null space.
Yeah, so what is it? It is the set of all vectors such that T of x comma y comma z is 0, 0, 0. So it is the set of all such vectors such that x plus y plus z is 0, z minus 2y is 0.
0 and 2y minus z is 0.
So I have a system of linear equations. 1, 1, 1. 0, minus 2, 1. 0, 2, minus 2. So clearly these two equations are the same, right?
Yes. So the third value will become 0.
0, 0, 1, minus half, 0, 0, 0. So what is the rank?
2.
Yeah. Nullity is
1.
Nullity is 1, so not 1 to 1.
Yeah, clear.
And rank is 2, not on. Okay. So now I want to find out.
No, can you please stop? Sorry. Now rank is 2, so not on 2 you are telling. Nullity is 1, so not on, not 1, 1, that is clear. Because nullity has to be 0, then only. Here, how you made that decision?
Rank is 2, not equal to dimension of codomain.
Okay. Yeah. Now it's. You are comparing with the codomain. Yeah.
So from here, let's get back. So it is the set of all vectors which satisfy x plus y plus z is equal to 0, comma z is equal to 2y, right?
Yeah.
From these two equations, I get z is equal to 2y. This is x is equal to minus y minus z, minus y minus 2, minus 3y, right?
Yeah.
So I can write it as minus 3y, y, 2y. Clearly nullity is 1, so there should be only one free variable. We got only one free variable, right?
Nullity, okay. Yeah.
So basis.
Minus.
We can choose.
-3, 1, 2. Correct.
So
Dimension
let's
of
see
base.
what the question is. Nullity we have found out. Z is equal to my, x is equal to ny. We have to find out m and n. That also we have found out.
Okay.
And then, okay, fine. What about the range space? Basis for range. How will we find out basis for range? What is the range space? Set of all a comma b comma c, which is equal to t of x comma y comma z, such that x comma y comma z is in the domain, right? Okay, R. So this is the set of all a comma b comma c, such that it is equal to t of x comma y comma z. What is that? X plus y plus z. Sum 2y minus z. Z minus 2y, 2y minus z. Z minus 2y, 2y minus z. So what does this say? A should be equal to x plus y. Or we can write it as a system of linear equations. X plus y plus z is equal to A. Z minus 2y is equal to B. 2y minus z is equal to C. So 1, 1, 1.
A.
0 minus 2, 1, B. Clearly, B should be equal to minus C, right? From the last two equations.
Yeah.
Yeah.
Minus 1, C. So 1, 1, 1, 8. 0, 1. Minus half. Minus B by 2. 0, 0, 0. C plus B. Right?
Yeah. Yeah.
So for this to have a solution, B should be equal to minus C. No other conditions, right? Because this is the only zero row. For it to have a solution, B should be equal to minus C. This term has to be 0. No other conditions. Right?
Yeah. Yeah.
So the range is set of all A comma B comma minus B, such that A comma B belongs to R. Right? No condition on A, no condition on B. C has to be minus B.
Okay.
So is it clear that the rank is 2 and the dimension here?
1.
1, 0, 0 and 0, comma 1, comma minus 1, is it?
Yeah. 1, 0, 0, 0, 1, minus 1. This is the basis. Which of the following is or are a basis of range of T? Okay, there are multiple options. You should check if everything is, you have to choose all possible bases. So 1, 0, 0, 1 minus 1, 1, 1 minus 1, 1. It satisfies, right? This is the only condition I want.
Yeah.
Yeah.
B is equal to minus C is satisfied here and all. Here, these two, it is not satisfied. For 3 and 4, it is not satisfied, right? B is equal to minus C is not satisfied in the second vector.
Yeah.
So these two are eliminated in the first. What is it?
Sorry, complete, please complete. I'll ask the question later. It's okay. Sorry, I thought you were.
So B is equal to minus C is satisfied in the first two options in both the vectors. And both are linearly independent. So this forms a basis, right? The first two options.
Yeah.
Yes.
Yeah, that's it.
Yeah. So for one-on-one, we can actually basically when you found the basis for null space, we can go with what can be termed as a homogeneous system, as in AX is equal to 0. And we take a non-homogeneous system and solve for this basis of the range. Is that fair to say? because we are assuming it as A, B, C.
Yeah, you're trying to solve this.
Yeah.
You're trying to find those values of B.
Yeah.
Means you want to make sure for every B this has a solution for onto. That's
yeah. Okay.
Here, ma'am.
This was my question earlier, madam. Thank you, madam. Yeah.
Hello, ma'am.
Yeah.
Hello, ma'am.
Yeah. Please.
Here, ma'am, we get B is equal to minus C here. One expression. So how do we check onto here, madam? B is equal to minus.
No, we have already checked onto. Rank was 2, so not onto.
But in previous example, you will check also this method.
Which one?
From this, yeah.
From which?
From equation, madam, like T, X, Y, Z is equal to A, B, C. You have checked now onto like this. So we can check here also onto in that.
That's what we did here also, no? This will only for these values. Only when B is equal to minus C, there is a solution. But I can find vectors like this, no? B is not equal to minus C. So for these vectors, there is no pre-image.
Ma'am, so it doesn't have to be 0, 1, minus 1 only. It can also, we can have some value in the...
Yeah. As long as they are linearly independent, it is fine. Linearly independent and satisfies this condition.
Can you scroll up to the null space, basis for null space, madam? That way it's all. Oh. Null space is in the same. Null space is a part of the range itself, isn't it?
No. Null space is a subset of the code domain. Null space is here.
Yeah.
Range is here.
Range is here. Okay. Sorry. That was unfortunate.
Okay, so is it clear what we did?
Yeah.
Can I ask a question from the reflect with us?
Yeah, sure.
In the week 7, I could not understand. Reflect with us the first question.
Did you watch the live session of week 7?
Yes, ma'am.
I had explained this problem completely there. You probably missed that.
No, I have gone through. Still, I have a doubt regarding why this f x y z is x minus. Somewhere I have trouble understanding.
Can you watch that? And if you don't understand, ask me on Friday, because it's a step-by-step process, no? So
I did.
This is the final step.
I already did watched it. That's why. Yeah.
So
if you just say briefly, maybe.
Did you understand how we got T?
T.
Huh? Did you understand that?
I understood L1 and L2.
Okay.
L2. So
and then once you know the linear transformation on a basis, you know the linear transformation completely, right?
Yes.
So from that you can get T. That is this step. From here, you know T on a basis.
Yes.
So you will get T. Once you get T, you just have to add it with that whatever value. 201 or something. Yeah, 201.
Once we have these values 0, 1, 1, we have to solve for f of u.
No, you solve for T and then add T with this value 201. That's all.
201. So that's what called affine subspace.
Yeah, means this is an affine mapping.
Yes, it's an affine mapping.
That's why you get this 2 here and 1 here, 0. So 2, 0, 1 is added. That's it. This is your T. The last option is your T. You have to add 2, 0, 1 to it to get affine map. F. It's given here. No? F of u is T is 201 plus T of u.
Can you, is it possible, week 8, only the highlights, like a power play, just 15 minutes, can you close it off? What topics? Because
Week 8. What is an ortho? Okay, maybe from inner product.
Ma'am, one request. I think week 8 we have discussed pretty much all things, but the last lecture we haven't discussed.
Only power play.
But the last lecture, that rotation one, if you can give a little bit more emphasis on that.
Okay. What was there in rotation? I don't remember.
No.
That
I think Shubham had explained.
Yeah. But he said that you have to remember a couple of things, that whether
Yeah,
it is
you
given
actually
3
have
cross
to
3.
remember.
Yeah,
If it's
so
rotation,
if you can give some hint that what to remember, what to not, and because it's not pretty much clear, because in lecture it is not given that what to remember, what to not, and what to expect
you have to remember those matrices, that cos, minus sign, whatever. I don't remember. Actually, there is a way to think the matrix, but that's too much out of scope of this course. So
yeah, that's what even I asked him also, but maybe he forgot or something.
Okay, no. Week 8, just video wise, not full description. What is what? Then I will try to.
I'll start from inner product. Means from there it's a separate topic.
Yeah. Then we can relate all these things.
Yeah. We'll close by 11:15 around, because the studio team will be waiting for me to finish the session.
I had a couple of doubts, but
okay, fine.
After that,
so what is an inner product? It is a function.
Multiply vectors, each element in the vector, and add the total.
No, that is dot product. That's one of the inner products. Inner product in general is a function from V cross V to R which satisfies 4 conditions.
4 properties, right?
This is always greater than or equal to 0. This is equal to 0 if and only if
B is equals to
0. V1 plus V2 comma V3 is V1 comma V3 plus V2 comma V3. Alpha V1 comma V2 is alpha times V1 V2 and V1 V2 is equal to V2. So if all these conditions are satisfied, then the function is called an inner product. So we had discussed a lot of examples on inner products. So using inner product, you can then we define what is a norm. This is defined using an inner product. The norm is a function from V R. So given a vector, you associate it with norm of a vector. The norm generalizes the notion of what is it called? Distance, length of a vector. So it is a norm if it satisfies these properties. All these concepts generalize. Okay, so inner product generalizes dot product. Norm generalizes the length of a vector. So the length is always non-negative. Length is 0 only if the vector is 0. When you scale a vector, its length is going to be mod alpha times the length of the original vector. And then the triangle inequality. When you add two vectors, that length is going to be less than or equal to sum of the lengths. So a norm is a function satisfying these conditions. So to check something is a norm or not, you have to verify all these conditions for all vectors in the vector space. So this also we have discussed a lot, and this is norm. It is the square root of inner product of x with itself. So this is norm of a vector. Okay, this is norm from the inner product. You can define various norms. From the inner product, you can define a norm. That is this, square root of inner product x with itself. And then, yeah, using inner product, orthogonal vectors. Two vectors are orthogonal if their inner product is 0. So in R2 or R3 or anything, orthogonal means perpendicular. So two vectors are perpendicular if the angle is 90 degree, which means the dot product is 0. So generalizing that concept, we have orthogonal vectors, which means that their inner product is 0. And two vectors are, or any set of vectors, is orthonormal if they are orthogonal and x and y are unit vectors. And how do you get unit vectors?
By dividing its norm.
Yeah, this is always a unit vector. So if you have a vector which is not a unit vector, if you want to convert it into a unit vector, just divide by its norm. Yeah, and then we have the Gram-Schmidt process. So I don't remember the formulas, or maybe let me try. If I have a basis, I can always convert it into an orthonormal basis. What is an orthonormal basis?
Inner product is 0 and norm is 1.
It is a basis which is also an orthonormal set. That is, every vector, every pair of vectors satisfy this property and all vectors are unit vectors. Then we say it is an orthonormal basis. How do we do it? So V1, okay, we'll construct from V1, V2, Vn. We'll convert it into W1, W2, Wn. Here it will be an orthogonal set. And then we'll convert it into U1, U2, Un, where it will be orthonormal. So W1 is V1. U1, this is already orthogonal. So to make it orthonormal, I just have to divide by norm, right? So W1 by norm W1. W2 is V2 minus the projection of V2 on U1 in the direction of U1. Yeah. So this is the projection of V2 on U1. And U2 is W2 by norm W. W3 is V3 minus projection of V3 on U1 minus projection of V3 on U2. And U3 is W3 by norm W3. Like this you do, and then you will end up with an orthonormal basis. This is the Gram-Schmidt process, and in between we used projection. Yeah, projection is just a formula. How to project a vector onto a subspace and all that. That's just a formula. Okay, then what did we have? Orthogonal transformation. A transformation we considered only from V to V is said to be orthogonal if TU TV is equal to UV. It preserves distance. That's all. This is an orthogonal transformation. You just need to check whether this is satisfied for all u and v to check whether it is orthogonal or not. So to show something is not orthogonal, you just have to find a pair of vectors for which this is not satisfied. And an orthogonal matrix is a matrix that satisfies A transpose is identity, A transpose A is identity. So for this course, this is what we take. So that is why we are considering only square matrices. So this happens. So this is the gist of the inner product part. I had also discussed when one of this is satisfied and the other is not satisfied and all that. So that you can go back and check. In that case, A will not be a square matrix. If A is a square matrix, these will be satisfied simultaneously. All that was explained in detail in that session. So this is the power play of the portion after inner product.
Yeah. So meaning to say that 15, 16 pages along with your that announcement video for week 8, that will cover, right?
Yes, so we have covered everything, right?
Okay, I will catch from this. Okay, thank you.
Yeah, so we are left to do matrix of a linear transformation, equivalent matrices and similar matrices, affine transformation. This we can easily cover in 2 hours.
2 hours, yeah. Because it's revision 2. This is not the first time we are going to do. Yeah.
Ma'am, what is the next class?
What is it?
What is the next class? Next revision?
Friday at 6.
Okay, ma'am.
Friday at 6, right? Oh, yeah. Okay, 6. Okay.
Friday, yeah, at 6.
And you try to reset the mock if possible.
Yeah, I'll check that.
Okay, thank you.
Okay.
Ma'am, in one of your tutorial, can I ask something?
Yeah, please.
Yes, ma'am. So in one of your tutorial, I've seen that it is written that dimension of V is equals to dimension of W, then T, and when T is 1, if and only if T is on 2. So the converse is also true, or it's just this one is true?
It is.
Converse is also true.
Yeah, it's if and only if and only. Here. T is not 1 to 1 if and only if it is not on 2. This is all happening because of the same dimension.
Same dimension, right?
Yeah.
So converse will also be true, right?
Yeah.
Ma'am, one more thing, just a theoretical type of doubt. In one of the sessions, we were discussing about the matrix of equivalence matrix.
Okay.
So how we can calculate all this? So when we are calculating equivalence matrices, then could we take all the combination of basis of domain and codomain basis like gamma 1, beta 1, gamma 2, beta 2? This. So matrix, can we take all the combination, or is it fixed one? Because in that session it is written particularly that T gamma 1 beta 1 will be similar as T beta 2 gamma 2, I guess.
No, you can take anything. For equivalent matrices, anything.
Yeah, we can take any permutation combination in that, right?
Yeah, but for similar matrices, it should be same. Beta, gamma.
Anyway, similar matrices is so complex. So.
Yeah. It's more difficult to handle. Yeah.
But equivalence we can understand. I think.
Because it's characterized by rank.
Yeah. Thank you, ma'am.
Yeah.
Using eigenvalues, how to identify similar matrices?
Even using eigenvalues, you cannot tell similar matrices. There is no characterization for.
Similar matrices have same eigenvalues, right?
Yeah. But you cannot tell if they have same eigenvalue, they are similar. That's not true.
Okay.
It's so complex. It's so complex.
Yeah. These two matrices are not similar. but they have the same eigenvalues.
Eigenvalue.
Yeah. Okay, then.
Yes, ma'am.
There's
Thank you,
no
ma'am.
more
Thank you, ma'am.
questions.
Very much.
Thank
Good
you,
night.
ma'am.
Thank you, ma'am.
Good night.
Thank you.
Thank you, ma'am,
Yes, ma'am.
for your
Bye.
patience.
No problem.
Good night, ma'am. Thank you.
Good night.
Ma'am, please share this document with us.
Sure, sure. I'll do it now.
Okay. Thank you.
Yeah, good night.
Good night.